Hello, hello, check, bro. Hello, hello, hello. Hello, can you hear me, bro? Hello. నా అంటే నువ్వు మాట్లాడు నువ్వు మాట్లాడాల్సింది.
IIT Tirupati. You can this one. You can copy that and paste. Hmm. Just paste Control V.
Testing, testing. Yes, testing. ব্যাটার দূরে ছিল কিন্তু
Good morning, everyone. May I request all to sit, please? Take your seats. Okay, so I guess while the people are coming, we can start our program so that we can easily manage the time. Let me start by greeting all of you for this event. So as you know, we are conducting this event in association with the ISRO team, and all the members are here. So without taking more time, I request all our guests and Professor Raghav Rao to please come and light the lamp to start the program. Yeah. May I request a volunteer to please help? Thank you, everyone. May I request Professor Raghav Rao, Professor in Chemical Engineering and also our Dean Administration, to please come and give the welcome address.
Sabhaya Namaha. Good morning, everybody. Today's chief guests and chiefs dignitaries who have come for this function, Dr. Shrikant, Dr. Bharat Kumar, Dr. Srinath, and Dr. Shankara, and head of the department, Dr. Ritesh, physics, and my dear colleagues and my dear students. It was a great occasion today. We are celebrating the success of one of the great scientific achievement that has happened in recently. So I extend a warm welcome to all of you. I was learned that some more young students are on the way. I thank the organizers for giving me this opportunity today to be with you in the function. I wish our director, Professor Satyanarayana, is here, who could have also relished the exciting discussions, deliberations that take place today. It is very thoughtful of our colleagues at the Department of Physics to hold this event. It is very timely and inspiring because especially for the young brains who are the future of our country. Normally, when we say that for any achievement to encourage people, sky is the limit, we say. But our honorable scientists have shown that it is not the limit. Space is the limit, or in fact, space is limitless and boundless. That is the arena where all the young brains should explore in future. We can clearly see that we could reach moon, study Mars, explore even the sun. So this is the current status. If you look back, exploring perhaps is the basic nature of human beings, maybe even the animals. We started long back exploring on the land, sea, identifying different countries and different places of opportunity. But once rocket technology is developed, we started exploring even the space. Though it was started long back, maybe if I can look back into down the memory line, we can see that the great visionary, Dr. Vikram Sarabhai, who is the father of our space mission, it started long back. However, maybe during the later years, it has been a little bit slowed down in the country and West has taken over. One reason could be it is a very expensive research activity, but you all agree with me that it is worth the effort, because you look at the Apollo mission that has happened, which opened up several areas, for example, chip industry. So that has become the most popular now, and even the small country like Taiwan, after perfecting this technology, is dominating the world. So that kind of situation, so even in India, small industries also are participating, startups are participating in contributing to this thing. Our space program, if you look at it, once we launched these satellites, immediate applications we could see. We could see it is in the communication and education. Doordarshan has taken over All India Radio. So that was a huge difference that made single technology. Remote sensing in agriculture has gained. Our our colleagues may correct me. I understand that in remote sensing, India is one of the leaders. So now, through this Chandrayaan, it has demonstrated not only the technical excellence, but also economic prudence. No doubt, it is the victory and glory for the scientists of space mission, but it is a victory in proxy for all the scientific community at large in the country. In this, not only the government agencies, generally government agencies like ICR, CSIR, DRDO, ISRO, they used to be construed erroneously as white elephants. But I belong to CSIR before coming here. But such armchair critics are silenced with this great achievement. Even the private industry. See, private industry, if you look way back, even the Godrej started contributing for the engine design. And many private players, even when recently we have been to IIT Madras, in their technology park, we could see many startups working on advancements in propulsion, design of equipment, design of rockets. That was very heartwarming. In fact, at the moment, we have end-to-end solutions in the country. So that makes us very, very sufficient, self-sufficient. So it is indicating that, as the name suggests, the opportunities are immensely infinite. It is proving the concept that make in India. Not only make in India, it is make in India for the world. We are able to contribute at the world stage. Even government agencies, you look at it, HAL, the combat aircrafts, again in collaboration with CSIR laboratories, PDL, BEL, Bharat Electrons Limited, they are producing the electronic components and exporting even to Israel, which is a technical giant. So government is encouraging this environment. The spirit is buoyant. Perhaps such achievements are also rubbing onto the other areas. Economy is going, our international status is better. All these aspects are reflecting in the body language of people itself. I mean, that's my perception, or you can also tell me. Even if you look at our cricket team, the aggression, the body language is totally different. We won the matches before, but not with this kind of dominance. So with this great achievement, India has become the 4th country to reach moon and 1st country to reach the South Pole. It is a great exploit, a landmark achievement. However, it is the beginning of a long, successful scientific journey to achieve many more such laurels. Nothing succeeds like success. I conclude while wishing all the best for our scientists and the young students, a successful achievement in their scientific career. Jai Hind, Jai Bharat.
Thank you, sir, for the very nice remarks and appreciation. So before we invite our first speaker, I want to say a few words about the genesis of this program. So we all remember the historic day. In fact, the Indian space science program has been a very successful program and always make us proud in various fronts. And we know that on 23rd August, we see a historic day where the soft landing was successful for Chandrayaan-3. So I echoed with Professor Raghav Rao, and actually Government of India also announced that day as a National Science Space Day. And from that onwards, there is a good curiosity among the students, faculty members, staff, and also nearby school children to know about these missions more detail. They must have reads here and there in news. So we thought to conduct this event to bring out some scientific and technological aspects behind these missions. So we have chosen two, which are very recent and ongoing mission, Chandrayaan-3 and Aditya L1. So one is to explore the moon, another is to explore the sun. So our experts will focus on these two missions. We have also organized one session in afternoon, which is a dedicated section where you can directly interact with the scientist from ISRO, and you can ask questions and get more details, whatever you like. Before that, I also want to say a few words about our Department of Physics. So Department of Physics started its journey along with this institute, and we have started offering the courses to VTech first year, common courses. Then we have in 2020, we started our MSc program, and it has been very successful. And we are also planning very soon to offer an engineering physics program, which is already approved by CNET. It may be started in next academic year. Apart from academic front, the Department of Physics is doing very good at research front. We are having very good research laboratories and also very dedicated faculties who is doing world-class research. We have faculties which are doing research, both theoretical and applied aspects. And most of the research are in our department currently focused on atomic molecular physics, quantum optics, plasma physics, ultra-fast spectroscopy, high-energy physics, quantum materials, condensed matter physics, theory and experiment. And we also have very good PhD students who work along with us, and the department is growing very fast. And any of you, I know many of you are coming first time to the campus. If you want to visit any lab or if you want to interact with us, please feel free. We'll happy to share what we are doing here. With this, let me take the privilege to introduce our first speaker. It is an honor to introduce him, Shri M. Shrikant. He has been working in ISRO since last 19 years. So he has a vast experience in mission design, spacecraft mission operations. He was also he is also the mission director in both Aditya L1 and Chandrayaan-3 mission. He's from UR Rao Satellite Center, and his mission operation areas are Space Operation Manager for Mars Orbiter missions, Deputy Mission Director for CH2, and currently working as Mission Director in CH3 and Aditya L1. He also received many awards. Few of them are ISRO Young Scientist Award 2012, and then SAI Team Achievement Awards year 2013. With this brief note, I would like you to invite sir. Over to you, sir. Caller mic.
Good morning, all. It gives me great pleasure to be in front of the very young generation who are going to be our future for our country to prosper many ways, and at a very premier institute, IIT Tirupati, where the bubbling engineers who are going to serve the country as well as serve the world in many fronts as an Indian. So it gives a great pleasure for me to be part here and talk and deliver a lecture about ISRO's major achievements recently. One is Chandrayaan-3 and is Aditya L1 mission. These are the two important missions which have shown the world, and as Sir has told, it has increased the yardstick of Indian standard in the all over the world. So before I go to the technical presentation of Chandrayaan-3, I like to thank Satyanarayana sir, who is director IIT Tirupati, and Raghavarao sir, dean, and the senior faculty members and my senior colleagues from ISRO. Good morning all. So coming to the Chandrayaan-3 classic example for successful lunar landing missions. You are seeing a rover which has rovered on the lunar regolith for 100 meters after the post landing. This is one of the major achievements which you can count for years to come. So before I go to the presentation, I want to give a glimpse of the various countries or space agencies who tried for a successful landing on the moon surface. Successful attempts they had and how much struggle they have put forward to get a success. You can see on the moon here where they are indicated different countries like USA, that is America, and Russia and India, so and China. All people have tried to land on the moon surface at different polar side regions. If you take on the northern side, they tried at equator, they have landed majorly equator landings they have done, and southern side also they have done landings. But now there is a huge rush to reach the southern pole. Everybody is trying to reach southern pole. Why? I will answer it in few slides coming up. So at present, before the US had a successful landing, they had 3 unsuccessful attempts. USSR had 11 unsuccessful attempts. India had 1 unsuccessful attempt, that is Chandrayaan-2. But we have a proper orbiter which is still working and it is giving very good data with respect to the science observations. So we had a failure only in the landing, not in the orbiter mission. So that mission is still going on. Now, after that, before our Chandrayaan-3 landing has happened, we had few other agencies, countries which are tried for landing was Beresheet Israel, Hakatu R1 from Japan, and Luna 25 Russia. Actually, these people also tried to land, but they were unsuccessful. And few days before Chandrayaan-3 landing, the Luna 25 also was supposed to land some 100 kilometers away from our landing site where we are planned, but they had some technical issue, so they lost the satellite. So what this slide shows is landing is a technological complicated marvel. It's not so easy to do a successful landing. So we have been successful in doing the landing in our second attempt and also moving the rover on the moon surface. So these are our 2 things which were shown. Yes, we can meet it. Coming to the objectives which I told, to realize a lunar lander rover capable of soft landing on a specified lunar site and deploy a rover to perform mobility and science experiments on the lunar regolith. This is the objective of our satellite as defined by our system, which is precise, safe and soft landing. I will explain the precise, safe and soft landing in my next slide. The journey of Chandrayaan-3 starts not from only realization of Chandrayaan-3 it starts from Chandrayaan-2. So Chandrayaan-2 is our precursor for Chandrayaan-3, which has given us a lot of understanding or an experience on-hand experience, in-orbit experience, you can call, how to handle the complexities and how to handle the things in orbit. It has given us a lot of knowledge. Apart from other missions like Mars orbiter mission, also one was there, and Chandrayaan-1 also there. We have done a many orbiter missions around the moon, but landing mission was Chandrayaan-2 followed with Chandrayaan-3. So our composite formation, when we say this is a whole structure which looks like a whole satellite around, it is 4-ton satellite composite, which was formation 23rd June 23, and movement was done to the launch vehicle assembly on 4th July 23, and launch was on 14 July 2023. So after launch, the satellite is injected by the whole satellite as a composite. When I say it is including the propulsion module, okay, it's equivalent like an orbiter we can call, but we named it as propulsion module because here the objective was of the propulsion module was to take the lander to the moon's orbit and separate out. So that's what its job. But in Chandrayaan 2 orbiter had some payloads for imaging, so its objectives are different. So that's why we named it as propulsion module. Then we have a lander module which is having lander plus rover inside. The whole composite was lifted and injected by our launch vehicle into an orbit. Then when come to the major phases, see, before the landing happens, we have different phases of the mission, and each phase is critical in its own. When we say one is launch phase, which launch vehicle has done already its job. Now earthbound phase. When I say earthbound phase, because our launch vehicle has a capability to inject the composite into earthbound into an orbit of elliptical orbit around 200 by some 36,000. It got injected. After that, a series of burns using the propulsion module propulsion system were carried out, and you can see here the different burns were firing at the perigee point, that is the nearest point to the Earth, where the velocity of the whole spacecraft is more. So when you add velocity, it increases the height of the size of the orbit. So different burns were carried out. Around 5 burns were carried out. Then after the 5 burns, we have something called trans-lunar injection. Then we have, after that, followed with a lunar orbit insertion. Means it gets into the captured by the moon's sphere of influence. Then again, we have series of burns for reducing the orbit height, because our objective was to come to a circular orbit of 150 by 150 around the moon, then start our lander activities. So till that stage, our propulsion module has done its job. So this the earthbound phase, we have done the what I explained. Then trans-lunar injection, lunar orbit phase insertion, lunar bound phase. After this phase is over, now the lander got separated from the propulsion module. Lander, before landing, what is the requirement? That landing systems which are going to be used for descent purpose has to be qualified, assessed in their performance, whether they are going to work the way we want, or there is some anomaly, or then some fine-tuning of the configuration required. All this assessment has to be done. So we have done that assessment in this 150 by 150. Then we carry, at present till now we have used propulsion module, propulsion system only to carry the burns in raising the orbit or reducing the orbit. Now the lander has its own engines, which has to be validated. So we have done 2 deorbit maneuvers using that engines at different throttling regimes, so that our engines which we are going to use for descent purpose are working in the proper way, has been assessed, and we got into an orbit of 100 by 30 kilometers orbit. So at 100 by 30 kilometer orbit, our descent starts. So you can see a landing happening on the moon surface on 23rd August. So these are the glimpse of the whole story of Chandrayaan 3. Yeah. That was a glimpse and a story of Chandrayaan 3. Now coming to the Chandrayaan 3 configuration drivers. See, when we start any new project, what we should do, or what all of us do is, we'll see what experience we have with our own resources, or what other contemporaries have done. All put together, we build our knowledge base, the failures, what happened, and what is the lessons we learned from the failures, and how to overcome the failures, and what strategy has to be followed. All those things has to be worked out, because we want a successful mission, because we are going after a failure. So there was no scope for us to do another failure. We had to be success. So for that, all our teams last 4 years have done day and night meticulous work, ensuring that only one objective, successful landing and moving the rover on the moon surface. These are the 2 objectives which every one of the team member had in their mind, and they worked for that. So when we say Chandrayaan 2 heritage utilized, Chandrayaan 2 experience what we had during landing, that data was taken from Chandrayaan 2, because when descent was happening, we had a telemetry data. That telemetry data was used, and using our ground simulations. My fellow colleague Bharat sir will cover about the guidance and navigation. I'll give the gist. He'll be covering further details. So Chandrayaan-2 heritage, we analyze the data and what would have led for the failures of Chandrayaan-2. We have simulated and we have tried to overcome that failure conditions by building robustness into our system for Chandrayaan-3 and doing a lot of tests, both digital simulations as well as in the hardware tests. We have done as much as possible to build our confidence that yes, there should be a successful landing. So Chandrayaan-2 heritage utilized, Chandrayaan-2 on-orbit experience addressed what is there, and robustness was built into the lander of Chandrayaan-3 using these two, and ground tests and simulations and new aspects were introduced to take care of further failure, any other which were the shortcomings in Chandrayaan-2, which I'll cover. And on-orbit testing and evaluation was introduced in Chandrayaan-3 better than Chandrayaan-2. All these things were made. The Chandrayaan-3 final configuration arrived, was considered, and we had a safe and soft landing. So when I say robustness, improvements in the sensors. See, when we say a spacecraft, its information is position in terms of XYZ and velocity XYZ. These are the information which are required for us any point of time. And during landing, we require height also. So these are the information which we require from our sensors. So what we had is one additional sensor we introduced, that is there's a Doppler velocimeter which gives us the velocity of the craft at any point of time. In Chandrayaan-2 we had image-based velocity sensor which was giving 2-axis information. But yeah, we did an improvisation in the Chandrayaan-3, building a new sensor, incorporating it in Chandrayaan-3 to have velocity information, all 3 axes at any point of time. What was new thing introduced? Then we have done improvements in the propulsion system. Then multiple mission paths to handle contingency improvements in guidance and controls. When we say we didn't want to build only one path, successful nominal path landing, we have built contingency paths for, when I told the first point in my first slide, precise and soft landing. See, whatever we planned was a 4 by 2.4 kilometers landing region. We wanted to have precise in that region, soft landing. But in case, because of some anomaly in the guidance on system or some sensor system or engine system, but 100% we should do a landing. At anywhere we should land. That's what our main objective. So for that, we have built n number of contingency paths into the guidance and navigation loops. Onboard OBC computer was designed to handle take care of these anomaly conditions. Onboard logics were built based on the sensor failure conditions or knowledge what it is getting with respect to the inertial navigation. All these things were done, built into the system and tested on ground, and to some extent tested in hardware, what is possible on Earth. So all these things were done. Then we had enhanced touchdown velocity limits, because when we're touching down the moon surface, the legs are going to take the shock. So the velocity has to be, they should be able to take the shock as well as the velocity, horizontal velocity and vertical velocity also should be within the limits. Otherwise, lander can topple. So that was the requirement which we enhanced the limits, which I'll cover in the next slides. Then NG software improvements have done, increasing landing area. In Chandrayaan-2, we had selected 500 by 500 two regions, which we wanted to land in that regions. But in Chandrayaan-3, what we did is we had enhanced the landing region to 4 by 2.4 kilometers. Means when we have a larger region, we have more flexibility to land. So that's what we did. And fuel level redundancies to take care of hardware failures. Overall system improvements were done. Then coming to simulation special tests, exhaust simulations, various platforms like 6DOF, oil, seals, hills, and hardware simulator. We had a hardware simulator on ground. Before we execute something in orbit, we are testing the command sequence and the procedures, everything on ground, and seeing that it is executing as expected or not. If there is some anomaly, we will be able to rectify on ground, change the sequence, and execute it on board. So that type of equivalent hardware simulator was built on ground. So then ICT, integrated cold test. All sensors and navigation were tested here using a helicopter. All the sensors were mounted on the helicopter. It was sorties were carried out. Different sorties were carried out for going to different heights, and the sensor performance and accuracies were assessed and validated with the expected outputs. All these things were done in ICT, integrated cold test. Then hot test, when I say, along with sensors, we brought the engines. integrated test was carried out for all sensors, propulsion, navigation, guidance, control system, closed loop test was carried out, and lander drop test. This is like a because we know that moon's gravity is 1/6 of the Earth's gravity. So we have the mass which landing is going to do. That mass was varied, and we have done the lander drop tests at different slopes on the landing time, because see, it need not be flat like this. Moon surface will not be flat. There will be some slope there. It can be how much slope we can tolerate without toppling the lander. It was less than 12 degrees. Like that, some sort of landing the slope was tested, and our lander legs, whether one leg touches, two leg touches, all these things were tested on ground before the actual this thing. So that gave us a lot of understanding of the system, their dynamics, and all the things. Then apart from this, we have done all these things on ground. But now, whatever we do on ground is one side of the coin. Other side of the coin is in orbit. In orbit gives a totally different picture for us. So we need to assess the systems before they are used. So in orbit testing and on orbit calibration of the sensors which are going to use for descent start were used, were done, carried out. Now coming to the limits, as I told you, improvements, there were additional velocity sensor was introduced, multiple paths were introduced, touchdown velocity limits were enhanced from 2 meters per second to 3 meters per second in the horizontal, 0.5 to 1 in one vertical, landing area increased, and all these things are already covered. So these are the changes I can tell what we done to bring the robustness in the system. Now coming to the landing area, this is the region which was selected of 4 by 2.4 kilometers, and the landing site was around 69.39 degrees south, and longitude was 32.34 degrees east. So this is the landing site which was selected, and in case we miss this landing site because some anomaly in the orbit, we had a backup landing site which is away 3 days from this. So we have built plan A, plan B for everything. This is how the whole system was designed to take care of the anomalies. Now coming to the Chandrayaan-3 mission elements, LMV-3, which was introduced by, as I told, it is injected in the orbit of 175 and argument perigee was 178, inclination was 21.4 degrees. Total mass around 3896 was the liftoff mass, and lander module was 1750 kg, and it was designed for 1 lunar day, that is equal to 14 Earth days. Then we had a propulsion module which mass is 2145 kg, and the major objective of this is to carry the lander module and inject the lander module until separation, and rover is 26 kg, and its life was 1 lunar day. And we only see the one thing is landing is one objective, but after landing we should do science. For that we have flown different host of payloads on both lander as well as rover, which has given a good knowledge or a good rich of science data for our scientists to analyze about and understand the moon's surface, which my sir will be covering about Chandrayaan as well as Aditya, few points. So coming to the lander instruments, as lander has landed at one place, the instrumentation of science data is constrained to that region only. But rover has an instruments which as rover can move. So wherever rover has moved and stationed, we have collected science data using the science instruments, in situ particle measurements we done using the science payloads on the rover. So coming to the module configuration, see, when we say a satellite, it shows you how different and how many systems are really involved to integratedly work together to meet the objective. If you see, there is an onboard computer where we, instead of going to onboard computer, I'll tell before that we have fuel and oxygen, that is our propulsion system. Then we have our RCA system, this is the whole propulsion system we have. Then power system we have. Then our telemetry, telecommand system we have. Control system we have, and inertial system is there. Sensors are there. RF system is there. So you can, and one shape payload has flown on the propulsion module, is an experimental payload. So you can see a host number of systems integratedly work together and meet the objective. So this is how the whole system is working. And because we wanted to optimize the mass of the whole composite, we have shared the resources of land resources were used by propulsion module. So like that, the actual control wheels, actuators were shared by the propulsion module. So this way, the whole propulsion module design was done. I think battery is not working. System hanging. Onboard computer hanging now. Yeah.
Can you check?
Yeah. Now that was the some host systems which was in propulsion module. Now you can see land had a whole another few more systems because it has to do a landing job apart from the lander on its own to control in the orbit. So it had again the sensors. I'll tell here also propulsion system is there, and we have sensors which are there: LASA, altimeter, LHEC, velocity sensor meter, LDV, inertial system, imaging cameras, altimeters. Then we have NGC system, the guidance, navigation guidance, control electronic system. Then our telecommand and telemetry system, solar panel for power generations, batteries, S-band RF systems. Then we have our lander imagers, payloads, and here you can see this star sensors, wheels, increment touch. So there is a host number of instrumentation, actuators, everything put together. Lander has been realized. Why? When we say lander's job is to do two things. One is it should control itself after separation from the propulsion module. So it has to be like an orbiter equivalent orbiting around the moon for 6 days. Then it should also have a propulsion system to reduce the orbit. So a propulsion system is built in. Then it should have the telemetry and telecommand system for communicating with Earth. What you want to tell the satellite should be able to command the satellite. And what is the health to tell to ground, telemetry is required. Then that is RF system's job. Then we have our control system, software, NGC electronics, then land imagers. See, there's land imagers also play eyes for us. What we are expecting, whether land imager, if you orient towards Earth, whether it's seeing the Earth or not, if it is reoriented towards moon and it images the moon, when it's seeing the moon or not, means it is like an eyes for us, what really it is happening and what we are expecting is happening or not. So land imagers have played a very critical role in our landing thing as well as pre-landing to show the thing that we would have seen many videos released by our organization. Moon when en route Earth images, moon images, and while landing, while descending was happening, how the moon was looking, and post landing, how when rover was rolling down, all these images were captured by the land imagers only. So it is telling you that yes, the job what you planned is happening correctly or not. So coming to the, till now I covered the systems which are there. So okay, before I go to the next slide, the rover. This is a tiny, I call this a rover toy because it's only 26 kg. But the job what it has done is exemplary because it has rode on the moon surface as well as it has collected the science data, and it has itself when it has reoriented the panel, we are reoriented the panel in such a way that power generation is there all the time, and the navigation cameras actually see rover has to move the moon surface means it cannot move unless you tell from ground how it has to move, because the moon surface who it is nobody knows, how the terrain is there nobody knows. We know only an assessment we have, but for a rover to move we should have better resolution images which can be done by its cameras on the rover. So I will be covering who it was done in the next slides. So coming to the descent profile, this is our major descent trajectory where we had 4 phases. One is rough braking phase where the majority of the velocity was killed. Then actual hold phase where we had taken the sensor updates, altimeter updates for control loop, guidance and navigation loop. Then fine braking phase we trimmed the velocity. Then module was made vertical and we had taken a vertical descent path, and we have done the LSDAC operation, that is our hazardous. See, when landing is going to happen, we have selected 4 by 2.4 kilometers. But we have already had our onboard high resolution camera flown on Chandrayaan 2 orbiter, which has given us a knowledge how the terrain looks there. So we had a knowledge, but still wanted to land at a more precise and safe grid where there is no hazard. So onboard what he has done is a camera is put which has operated and taken the image, and it is operated and told that yes, the grid where you are going to land is safe or not. That type of knowledge has come in the real time to us, and onboard computer has seen that yes, where it is going to land is safe, and it has landed. So that is how the system was designed. So more details Bharat sir will cover about this trajectory. Coming to the science instruments, as I told, we had a Ramba LP, Lagrangian probe on the lander, CHASTE and ILSA. These are three instruments which are flown on the lander. Then we had rover payloads, APXS and LIPS. These are the two payloads on the rover and SHAPE payload on the propulsion module. So apart from our primary objectives, the science objective to get the science data, we have flown a host number of instrumentation on these three things to get the science data. Now, as I told, coming to the rover, see, rover cannot move on its own. As I told, it has to be told how to move and from the current point where to move. So first, for that, what we done is we have put two cameras on the rover, which will see the region where rover is standing in front of it. So it gives us the data to ground. On ground, we have built a state-of-art software which will analyze the region where rover is standing in front of that. And when we say rover has to move, it is that it need not be straight. It can go in a like a snake. So we have built something called modes on board, like straight motion, in place turn. These are two type modes we have built on board. So to reach from one point A, where it is standing, to destination point B, how to move in terms of segments? You move straight 1 meter, in place turn of 10 degrees, then move straight of 2 meters. Like that, we can build a path from ground, from point A to point B. This type of thing was designed and tested and developed on ground. For Chandrayaan 2 it was developed, but Chandrayaan 3 we have executed it, and ground testing also was done for the same software. It was state-of-art software, and we have developed for the first time for our rover mobilities. So that was used, and we moved the rover from point A to point B. When you say it has moved from point A to point B, the destination point where it is going to reach, it should be free from what? It should be free from the, means assume that where you are going, there should not be shadow from the local region or a casting shadow from sun, because it's also depending on solar regeneration. If you go to a point where rover is going to stand, there is shadowed after some time, power generation will come down, and you should have communication with Earth continuously or communication with lander continuously, because our systems of rover can communicate with the lander only, and lander to ground only is possible. So one thing is, whatever data is being collected by science instruments on the rover, they should be downloaded, they should be transmitted to lander. Lander data, again, lander transmit to ground. So this is how a whole chain has to be built in, and power generation has to be ensured, and shadow should not be there. And where rover is standing, the slope should not be such a way that rover topples itself. Means you've gone to region, it is 20 degree slope there. Means by the time it reaches, it will topple. So we should see that the slope, what our final point of reaching is within the limits of slope is very less. And rover is, when the rover is moving also, the rolling and pitching, I'll assume that it is going and there is a slope of 20 degrees. It may topple in between only. So we should see that where rover is traversing in between to reach the final destination point. All these specifications and constraints are met all the time to meet the objective. Once it reaches the final destination point, now is the job of the science instruments. So science instruments have to operate. We have to operate our, as I covered the other payloads, APX and LIPS has to operate it. We have to get the science data. All these things we have to do. And apart from that, we had a rover imager on the back side, where it is capturing where rover is standing, back side of the image, how the moon surface looks. So all these type of instruments and imagers were built on the rover. And you can see totally the rover, when the point where landing has done, it is named by our Honorable Prime Minister as Shivashakti point. And at Shivashakti point onwards, the rover has rolled down to these different paths, and final rover point was this day, when at the end of the lunar day or Earth day, when sunset was happening, it has stood here, and it was made into sleep mode. It was put into hibernation mode. So you could see different paths here. See why this is first we went this side, then came back, again we went this side and came back, then we went this side. Why? The point is the region fully is good. When they selected the whole landing region, there's absolutely no issue. But the point is for rover, as I told, rover has its own constraints to move. So what happens is when it reached here, we saw a big crater coming. We thought that we can move it this side, try it move to this side. No, it is not possible. So in the knowledge what we achieved post landing, when rover has to roam on the moon surface, was a different experience. At one instant we reached to a crater, and we had to come, we were not able to come out of that crater because there was no path. Either we would retrace back. That is the only option left over for us. But what we felt is when we reach the big crater, let us get us the science data. So we did the science data there also. See, means when we are in crisis also, we have to think innovatively whether what is the advantage we can get from that situation. So we collected science data from there, then we retraced back. So this is how the whole path has been traversed by the rover mobilities in that 11 to 12 days. And so that's what I'm saying, 11 days, 100 meters we moved. And coming to special tests, ICT, IHT and land rock test. So we can see a helicopter and a sortie. Helicopter is going for a sortie where we tested our sensors. The interior hot test. This is a bungee rope with a crane which was carried out at Shar, Srirkota. This was done in Chitradurga. And lander leg drop test was carried out in our eyesight, Bangalore. So a host number of tests were carried out before the launch actually. So this gives the view of the flight modules, interior module and special test modules. So this much of hardware for different test purposes were realized, tested on ground and flown on orbit for a successful mission. So before I go to the next slide, any few points you want to ask about Chandrayaan 3? Otherwise, I'll go to the next Aditya L1 mission. You can ask, no problem.
Sir, one question, like in the first slide, you showed many landings have been done near the equator and South Pole landing is difficult. I want to ask, like, why is it difficult to land near the South Pole and compared to the equator? And one more thing, like, you showed that the landing site was nearly 69 degrees up to 70 degree, and it is not about like 20 degrees farther from South Pole. So why do we call it South Pole? And what was the previous landing site for Chandrayaan 2, and were there any corrections in that degree? Like, was it raised to more north side?
You can see here, I'll come from last to first question. Okay, last question was Chandrayaan 2 landing site was 70.9 degrees latitude, longitude was 22.7. You see 10 degrees longitude shift has been done, but lat is almost close. So we have fine-tuned our landing site also. Based on because earlier it was only 500 by 500, whatever we selected. See, before Chandrayaan 2, we had to depend on the external agencies for our landing region imaging data, like LRO, Selene and all. But now we have more flexibility because we have our own orbiter orbiting around the moon with a OHRC camera on that, where we could get more landing regions. We could do the analysis and we could select the best site. So with respect to Chandrayaan 2, this next question was, why South Pole? Why you are calling South Pole, you are saying?
I'm asking, like, why is it more difficult to land in the South Pole?
That is your first question. Before that, your in-between question was, why you are calling South Pole?
Yes, yes.
See, you know that this is the equator of the moon. Above this northern pole and southern pole. The pole region is exactly 90 degrees as you told. But when we say, we always say southern pole region. We never said South Pole. The wording is different. When we say southern region means below the equator, anything is southern pole only. Southern region. The pole is at this point. Thank you. So we are very clear when we say the southern pole region, not South Pole. See, there are future missions are coming, which is not now. near future it will be there, which is South Pole landing is planned, where because South Pole has many permanently shadowed regions where we can, there phase of water is expected to be there. There's a separate host number of instruments will come. That is a futuristic planning. At present, we are landed at Southern Pole. That's what I can tell. Southern region pole. Okay. Yeah. And landing at pole, why it is difficult? See, many people have tried it landing at equator. But the landing is not, difficulty is not only landing. Post landing, there are many other host requirements to which will come. Just for example, when you land at pole, the sun's motion, how much it will happen with respect to the landing site? Sun will move in two directions, both azimuthal as well as elevation. When we start at equator, sun is always at the almost available for you. So the region landing is not only important. The region post landing, what is the other repercussions? And now see, till now the northern region has been explored by many people. Equator has been explored, but South Pole is less explored. But there is a lot of satellites which are orbiting around the moon and are observing using their instruments, and there is a very good it's called anticipation, you can call, or knowledge with the people that there are some minerals which are available at Southern Pole region. So everybody is doing a rush to Southern Pole to understand the Southern Pole region characteristics and terrain characteristics, you can call. So that's why it is.
And so, like in terms of landing or in terms of trajectory, there is not much difference when compared.
It will
to
be different.
equator
It will be different. That sir will cover. Anyway, sir, I didn't I'm see. Sir is a guidance and navigation expert. He will also tell you more in details. So sir anyway will cover those points.
And one more question, like previously you mentioned that the mission lifetime is 1 lunar day, and when the sun set, that went to hibernation mode. So will it be reactivated in future, or it has stopped? Or
see, at present we have put both lander and rover to hibernation sleep mode, as you are aware. See, our whole design is based on the solar array power generation, not with respect to RTGs or nuclear isotopes, heating and all the type of technologies are not built into our system. But we have qualified some sort of tests were done on ground before flying. It should sleep, a logic was built in to sleep, wake up post landing, means post 1 lunar day. Okay, we can tell that it is still in hibernation at present. It will wake up or not, we cannot tell. I think we are trying our best. Whenever it comes up, it will come up. That's all I can say.
so it will come up on its own, like
Yes, it should come up on its own. Nothing can be done from ground.
Okay.
Hello, sir.
Yeah.
Good morning, sir. Actually, I want to ask, like, how do you decide about how many payload you should add in that rover or lander? Is it based on the mass of the whole design, or anything else is there? Because we can add various payloads in that.
Your question itself is having one answer. The lift off mass capability. See, if you are giving more mass apportion for your other elements, payload mass will be constrained. But it should be a trade-off between the payload mass as well as the our spacecraft bus mass with the propellant and all. So we cannot give very less mass to payload and tell it is of no much importance. But it's a trade-off between these two. So we have flown an instruments which at least can tell us what science, good amount of science can come out with the data what we are collecting. So we have tried to do the trade-off here. That's all I can say.
Okay. Also, I want to ask, like, when we land on the moon, there is a different condition rather than Earth we have, and when we do testing on Earth, so how can we say that it will work on this on the other planets as well? How do we decide that? Because the atmosphere on sun or on Earth is different.
Yeah. If just 1 minute, I'll show one video, then I'll answer your question there. first point, just why I came back to tell is, when you can landing is happening, some sort of dust is coming. So that is also one complexity in the design, because dust can go and impinge in the bottom surface. So we should make our thermal protection system as well as the bottom deck in such a way that they are not getting impacted by this dust. So that's how one new technology or new design has to be looked into. This is one of the complexity involved. Now what will happen? Landing is done. So your question is with respect to environment, what is going to happen? Take a rover which is inside the, like a baby inside the lander now. Once the ramp doors opens up, it is exposed to the environment there. So what has to happen? A modeling or a knowledge of what type of temperatures rover is going to experience should be known to us. So a model was developed by our thermal team, using the knowledge of Chandrayaan-2 as well as our models which were developed in the earlier missions. Using that, a prediction was carried out how much temperature they are going to experience when ramp is going to open up. Once it's going to open up, rover is on the exposed to the environment. See, now rover is exposed to the environment. The thing is, now rover is still not active. So their input is available from our team based on the simulation analysis, that within this time, you see, rover has its own battery. When the systems are active, only heating can happen of the rover. So we are given input, yes, within this time, you should make the rover systems active on the ramp, so that temperatures will not fall off the rover as it is exposed to environment. The cooling will start very fast. So this was the required input given by our thermal team. So we have to plan the rover system deployments autonomously. So for that, we built something called autonomous roll down sequence on in the rover. What you have seen in the earlier diagram was autonomous landing sequence in the lander. Now rover post landing means after lander is done, rover will roll down. So for that is a autonomous roll down sequence was built in. Once we give a rover on command, it itself, if ground communication is failed to lander because of something, we are not able to communicate, rover should do itself its activities. That a sequence was built in. So we can see a sequence of activities which will happen now. So the systems will get activated. Thermal system will start acting. Heaters will come on. Heaters will heat the system inside the rover. Temperature is maintained because battery power is available. So up to that portion, from rover on, panel deployment, rolling down, touching the moon surface, everything was autonomous. Only one rover on command has to begin from ground. That much autonomous sequence has to be built in the systems. You can see here one crater. Na? See what we have done, lander has done safely, but rover has to roll down, and after touching the moon surface, crater is sitting there, whether to go or not. That's the first challenge we are facing. Everybody is worried because rover has touched now, but because there is no other go for us, we have to go straight. So we have to move the rover. So for that is another real-time challenge which we got in. passed through the crater and moved straight and is waiting there. Now, the point is, once it moved, battery is discharging. It has to have charging. How it can charge? When it is panel is means solar panel is oriented towards sun. So you can see that in place turn happening now. See, you can see a shadow coming from the other side, this side. Sun is this side, so it's pointing towards sun. So full power generation is ensured. That is how this is one destination point has reached after rolling down. So this is how every mobility of the rover, at the end of mobility, we have to orient the panel, see the power generation is there, and we are standing safely with the rover at any point of time. This much was carried out using our state-of-art software developed at ISRO.
It's a wonderful to know the insights, sir. Thank you for coming and sharing your thing. Yeah, I'm here.
Oh.
I'm professor of civil engineering, working in geotechnical engineering specialization. I understand the lander landing on the moon surface and also the rover mobility. There are some studies have been done on the lunar soil and simulated that climatic condition and all. The capacity of the soil has been evaluated, and also the relative motion of this velocity of this rover also controlled. I think some sort of thing. Some lights, some information on this regard will be helpful. Thank you.
So as I explained you, rover is designed to do one in-place turn and straight motion. In-place turn and straight motion with move velocity of around, when this was on the rover ramp, it was moving, if I moved at 0.5 centimeter per second. When it has moved and touched the moon surface with 1 centimeter per second, we moved. So this is the velocity specific, because on board we have more capability, but as you asked, based on the terrain, the slip, because see, the soil, the terrain of the moon surface is not uniform every place. It depends on the what type of density of the crystallization is there of this soil, and the how the looseness of this there, all these things. So we had done an assessment on ground, a typical assessment. When we do straight motion, how much slip percentage is there? When we do in place turn, how much slip is coming in because of in place turn? So those numbers are available for us a priori to some extent, because then at the same thing when we did in the moon surface, this type of mobility with the velocity numbers, what I told you for straight motion, and 0.5 degrees per second is the in place turn rate when we rotated. So these numbers were assessed with the ground measured numbers. So we could get an updated what called a knowledge, really that much slip is there or not, which was used to compensate the further mobility. Because if the slip is not accounted, finally, because rover doesn't have any absolute sensors where it is standing to tell, we used to do everything a bookkeeping. Our ground, I told, state-of-art software, which is always keeping a bookkeeping of the position and orientation of the sun, of the orientation of the rover, where it is standing. So this information was fed into that software with the instrumentation, what are planned mobility and the slip information, what has been estimated in the previous mobility, accounting for the further mobility. All these things were done. Then only we were able to move the rover mobility, that many mobilities, around 40 mobilities in 11 days. Otherwise, what will happen is we will think rover is here, but rover will be somewhere else. That will not situation. But still, there are some errors. What we have is an at least 90% to 95% knowledge of the systems. What, because we don't have any absolute sensors on rover to tell that my position, like GPS. Yes, I'm here to tell either there is no type of thing on rover. So we have to do a bookkeeping on ground, which has helped us to keep track of the rover position and orientation of the rover. These are our specifications, which I told you with respect to slip.
Soil also been model, right? The lunar soil.
Actually, lunar soil model means a typical lunar soil simulant was developed on ground, where we use that, where we moved the rover in that soil and tried to estimate the slip, which was done with Chandrayaan 2 time, and the same type of rover. So we taken that numbers actually.
That was matching, right? How?
It was not exact, but some extent match was there. Almost I can call 90% I can call.
Great.
Okay, that is what is the thing.
Yeah. Thank you.
The next, okay, this is with respect to Chandrayaan 3. Now another dimension is totally a different Aditya L1 mission, which is a mission towards the sun at L1 at an L1 point, Lagrangian point L1. See, before I go to the Aditya's mission specifications, a small introduction about these points. See, this is Sun-Earth system where the L1 point is there, where the forces because of gravitational force of Earth and the Sun are balanced with the centripetal force. So anything you put here at this point L1, it will be at that point. So we have like that. We have 5 points. One is the point which is other side of the sun, L3, and L2 which is other side of the Earth, and L4, L5. These are the 5 Lagrangian points. But we have chosen, why chosen L1? Because we want to have observation of sun continuously as well as communication with Earth. This is a requirement for us. So that point, that is only possible when you put a satellite at L1 point. But L1 point is a fictitious point. Assume that I put a satellite exactly at L1. Whether you will be able to communicate? Anybody? No, because the sun's RF signal also ground station Earth on the Earth, whatever is seeing, it gets corrupted by sun's RF noise. So whatever you want to command, whatever you receive is corrupted. So we cannot put exactly a satellite at L1 point. It should be put avoiding the sun exclusion zone, what we call. That was put, a satellite was put around L1. How that orbit is defined? In simpler sense to understand, you put a potato at L1 center. How the potato is there, the circumference of the potato has 3 directions. One is in the X direction, one is in the Y direction, one is in the Z direction. So over the circumference of, or the surface of this potato, satellite is moving. So that you never get into the interference zone of the sun. But at the same time, sun is very far, so you can point towards the sun using the satellite orientation as well as orient the antennas for communicating with Earth. This was the design implemented in Aditya. So the satellite is already en route. As you are aware, satellite already has crossed the Earth's sphere of influence. Now almost it is around 16 lakh kilometers from Earth, but it will reach L1 point in the first week of January. So our instruments which are being used for Aditya L1 payloads already are commissioning is going on. We are evaluating the systems. So this is how it is going on now. Now, as I told, the major objective of Aditya L1 is to understand CMEs, coronal mass ejections, flares, and space weather. And our Shankar sir will be covering more about this CMEs and all about science for Aditya in the next presentation. And orbit period is around 178 days, and it takes typically 125 days return. Once experiment crosses to reach L1, it takes 125 days. So this is a trajectory. You can see here also we are injected the satellite, our PSLV has rejected the satellite. We have done a series of burns. Then we cross the Earth sphere of influence. We are traveling in like this, and it loop back and come back here. So this is the trajectory which our Aditya L1 is going to take, and we'll be in this L1 point, and we'll be defining an orbit around L1 point like this, and this is the sun. And we have a number of instruments. One question was there from one of my friend that payloads. When you say payloads, here we have done more mass has been given. It's a trade-off. For payload also is given equal weightage. So around 300 kg of mass allocation has been done for payloads. We have host number. We have both imaging payloads as in situ particle measurements payloads on the Aditya L1. Like 7 payloads are there. All these 7 payloads are going to be using for understanding sun's dynamics and doing the in situ particle measurements of the solar wind particles. All these things will be being done. Means it is being in process. By next year, Jan, when the insertion is over, our payloads also pre-commissioning, evaluation, everything will be carried out. Then we will have an solar observatory at L1 point, which will also one of feather of our for us, for all of us, that we have one observatory at one. Always people will put a satellite L1 point. Why? Because water, sun's CMEs are coming towards Earth. They can cause a damage to our communication systems, power grids, or anything. But they travel with the velocity of solar wind, not with the velocity of light. But if you have a satellite at L1 point, it will give an alarm to us because their communication travels with the velocity of light. So we'll get an alert if our system, not for us, anybody. Why they will put is that because of that. So if the alert is there, we can have some response time to take care of our systems. So this is one of the objective which people fly the satellites and put at L1 point, and also to study sun. These are the 2 things which majorly people do it. So This is with respect to Aditya L1, and thank you. I didn't cover more about Aditya because this topic, today's topic was with Chandrayaan. But anyhow, I added one slide because my colleague and my sir is going to talk about Aditya L1 science. So I have put one slide for Aditya L1. Thank you very much.
I know there are a lot of questions, but sorry, what we will do, we'll take this question answer where section is there. So before we go for tea break, we should thank Shrikant sir for giving such a nice talk and overview of both the missions. And I would like to invite Professor Murali Krishna and Professor Muthu Kumar to please come forward and our token of love to our speaker. Hello. Hello.
See, one question was asked by one of my, when I went to one of the interactive sessions by an IITian only. I really appreciate that. I am not able to forget that question. What was question asked is, sir, you do lot of projects, experimental things. Some stage you would have faced or reached where you don't find a way out. You will be in dark. What stand you take? How you go about? That was the question asked to me. That question that is not only technical, but everybody's life, whether technical, non-technical, this type of thing comes. So in case of technical things, what I tell is, see, if you are working as an individual, as a team, whole team is working on that, but still you are not able to find a solution. Means what? You're already, your thinking brains, what you have as a team is not able to find a solution for that. So approach your seniors or approach your senior faculty members or approach your friends who have an expertise, because he is not biased with the thinking what you are having. He thinks in a different way. So it might give a solution. I'm not saying it's 100% foolproof, but yes, some solution can come. So always try in that direction. You will get a solution for this. And one more point is, this is a pure non-technical. Everybody thinks that once we have done our +1, +2 or intermediate, I should tell here, there is a rush for computer science. Everybody wants to rush for computer science, AI, ML and all. But I request that every field has its own importance. Don't see that only money is one thing. Money is one aspect of the life. But I suggest you people should see that whatever work you do it honesty, hard work and sincerely. Some hard work, some hardships will be there in life. But if you follow these three things and honesty, if you are there, you will get everything. So this is one message to my younger friends who are here, who are doing their schooling and passing out now +1, +2 and going for engineering entrance and all, or who are already IITians who are doing their IIT, completing their this thing. So I tell, these are two messages, and put the country first before anything. Thank you.
Thank you, sir. So we'll take a very short tea break, 10-15 minute max, because we need to hear other talks also. I request everyone to please be disciplined. There are 2 stalls outside for tea. take your tea, and then come back again. Let's say 10, max 15 minutes. Thank you. Yes.
Okay. The turnout and green. Welcome back. It's on green color, right? It's on green color. Correct కదా? Green ante on kada? Sure. It's not. Dear all, I request all the students to take their seats. Welcome back to our second session. In the second session, we have Shri GVP Bharat Kumar, URSC, and he is going to speak on the control system overview of Chandrayaan 3. So first of all, I would like to thank you, sir, for accepting our invitation and coming here and briefing us. So Bharat Kumar received BE in Electronics and Communication Engineering from SRKR Engineering College, Bhimavaram. He obtained ME in Control Systems from PSG College of Technology, Coimbatore, Tamil Nadu. Since October 1999, he has been working with UR Rao Satellite Center, URSC, Bangalore. During his stay in URSC, he served the organization at different levels, namely design and control systems for Indian remote sensing and interplanetary satellite missions. He acted as a project manager, remote sensing mission, project manager for Chandrayaan 1, project manager for Mars orbital mission, deputy project director for Chandrayaan 2, and deputy project director for navigation guidance and control simulations for Chandrayaan 3 missions. He is presently heading 6 degree of freedom simulation division under missions simulations group control and digital area. Now I welcome Bharat Kumar sir to give his talk.
Okay. Thank you, sir. So good morning to all. I'm happy to see all the youngsters. They are showing good interest on how we achieved this mission. So this is a lander which was standing at Shiv Shakti point. Okay, this is almost 700 kg structure is standing at that point. As a normal person, if I think it is almost 4 lakh kilometer from here, and we don't know how the terrain and how to go and all those things we don't know. So it looks a very surprising and it is a magic how this 700 kg structure was taken to moon and safely placed at a designated site. So that was for a common person or it is outside, it is a really surprising. But as a team ISRO or team NGCA, we achieved. How we achieved, we are going to try to tell what are the difficulties and what are the challenges, how we started our journey and reached the designated point. With initially the Chandrayaan-2 setbacks, but finally we made our dreams true. Now you see that this is the Indian made, total system is made, designed and developed and taken to that point and placed there. Now South Pole region, almost so many agencies are attempted to reach the South Pole. Someone was asking why, what is the challenge going to the equator or South Pole. So initially in Chandrayaan-1, when the orbiter mission, but there was one payload. That time our ex-president Dr. APJ Abdul Kalam sir, he told, initial that orbiter, we don't have any plan to take any object to the lunar surface. But later, once the mission is started, then Kalam sir told that no, you have to take some of our Indian flag should be there on South Pole. That way, that Chandrayaan-1, we made a moon impact probe, MIP, which was dropped from the, separated from the Chandrayaan-1 orbiter, and it was descended, and it was like a crash landed on a South Pole. And after that, this Chandrayaan-1 also, this orbiter also, it has done his scientific experiments, and they found the South Pole is having a more of craters and more of, they found that region, the water contents or water deposits, it was observed. So South Pole, where more craters are there. So all when sunlight is there, with orbiter missions also we could achieve the science goal. When the deep crater where the sunlight is not there, unless if you go there and you do the insect experiment, it is difficult to get the water, all the mineral components what is having. So that was science community. They told that no, we want to go to the inside the crater where the sunlight is not there. There we can find some of the different creature or some things we want to study. So that was given more science interest, because the ISRO is running for the interest of science and the commonality or common people, what are the needs are we have to fulfill. So that way this South Pole was selected. Now what is the challenge between South Pole or equator? The terrain wise, if you see, the equator is a more or less very, some flat region is available. So when we want to do the landing mission, where we don't know what type of terrain, so it is very difficult to go. It is like this. If you see these type of craters are there, or this is a totally undulated terrain, it becomes very tough. If you are seeing that other, your 6-lane highway, that type of area is there, we are comfortable. As a NGC, we want to prefers the equator region where I am having a lot of flat terrain where comfortably I can go and land. But that is of not much use for the science community. So we have to go to the South Pole. So South Pole challenge is there. We are not able to get the suitable place to get the landing. So that already our mission director Srikanth has presented. So this is object wise, it is the same for all subsystems. If you see our lander system, we are having so many subsystems, like a control system is there, and propulsion system is there, sensors are there. But object wise, for everyone it is the same. So what is the object? To realize a lunar lander rover capable of soft landing on a specified lunar site and deploy rover to perform mobility and science experiment. So as a NGC person, what to infer from this one? So that means the rover has to do the science experiment. So I should make a landing should be where it want to do the where to do the experiment. So that means they will tell that I want to go to the particular lat long. There's some coordinates they have specified. You go there and so that I can do the science experiment. So for as a control system or a navigational guidance control system person, you should know that, yes, I have to go to the designated point, not like that wherever I can. So that's why it becomes I have to land. Suppose he is telling that you land here, if I land 5 kilometers away, that science experiment is of no use. So that way I have translated all these requirements to the NGC system requirements. So again, this rover is inside the lander. So it has to come out smoothly. That means if I hard landing is there, it may or may not come out. So that there will specify some of the your design specification. How much is the your touchdown velocity? Then only the rover can come, or all the instruments should be intact. So that comes for me as a soft, so that the impact should be less, so that the rover can come out and do the other experiments. And it should not, after landing, the legs should not break down, all those things. So system should be, see, you have seen now the structure, if you see, this is how intact it was. That means the touchdown velocity, what was specified exactly, it was smoothly is landed. Now one more term is there, safe. Yes, it is landed. It is smoothly, it is landed, but it has toppled. So nothing can be done. You cannot go and lift it. So that means I have to see that it has to be in a proper orientation. So when it is a structure, it has to be vertical, and it has to be should be too much, it is inclined. So these aspects, as a NGC person, we am seeing that based on this object, which is defined for the lunar mission. So these things we are getting that, yes, this is the objective is given. That means I have to have a precise, safe and soft landing. So then for the safe landing, already he has presented where the South Pole and what are the coordinates they have specified. You see that these are the coordinates. So these are all the intended coordinates, and we are landed halfway, this much only, 170 meters south and 300 meters east direction. We landed. So whatever the intended coordinates, almost close to that one, we are landed. Less than 500 meters is the very precisely we have landed. Now other constraints are there, how the landing site already we have gone through. Now if you see the terrain, see what terrain we want, 4 kilometers by 2.4 kilometers is the wide range, so that any dispersion is there. If you are not able to go there, because we are traveling very far of distance, and the dispersion, the deviation, I started from here, it may not reach the point where I want. So it would have deviated. So I should know that how much area is a flat area is there, or it is a boulder, what type of sizes are there, or craters are there. So we could get very difficultly this much area. Earlier in Chandrayaan 2, we could find the area 500 meters by 500. So that is because we have taken the help from the other agencies to get the lunar maps. Now when after Chandrayaan 2 orbiter success, what we got, we have our own data. So that better resolution data is there. That is actually the world-class information is there. That is no other agency is having. That way the orbiter, Chandrayaan 2 orbiter data is a full globe. I think by this time we might have covered the full globe 0.2 meter resolution. Yeah, 20 centimeter resolution data it is available. That no agency is having. That is the one good achievement in the Chandrayaan 2. So this is the equator, you will get kilometers. But here in polar region, this is the now Chandrayaan 2 cannot say it is a failure. It is some setbacks over there, but it is given a good confidence and idea where the mistakes can come or where the improvements are there, or system to be improved. So after Chandrayaan 2 failure, there was a rigorous review. What went wrong, why it went wrong, why the system was not behaved the way we want. One thing we have to remember, system never behaves the way you want. The way it is built, it will behave. So those aspects are what the experts and seniors are suggested, because almost we are there. Chandrayaan 2 is almost, it is successful, but some of the small setbacks are there. You correct it and go ahead. So that's why we took very less time. And why we took less time means not only the changes are, but all the team, same team continued. Because the one good thing is there in ISRO community, wherever failure is there, the same team will continue. Because they don't want to discourage the team. So opportunity is given to the same team. So our goal is only one thing. Yes, we have to prove it. It is we had a failure, but we have to prove to the community, yes, we are technically strong and we can do it. That was the motivation, and each and individual has put their full effort, and everyone wants their system should not fail. So they attempted each and every point where it can go wrong, and they ensured that, yes, my system should not misbehave, or my system should not have any deviation with respect to my design numbers. So what all things are required, everything is done in terms of testing or in terms of analysis, all those things are done. So some of the improvements we saw is earlier what in the time frame of Chandrayaan 2, it's supposed to be, see what is our requirement, any landing mission, what we are going to do is, one object is here, I want to take to some designated, there I want to land. So what I have to control? So where is this position? First I should know where it is. With respect to what? I have to define some coordinate frame. Suppose if I am taking this as a, generally we'll take this object is going in a three-dimensional space. Okay, I should have, if I am telling that this is a coordinates wise, what you will tell? X, Y, Z. X, Y, Z with respect to what? I can define, suppose this corner, one orthogonal frame, I will take three axes, all are 90 degrees. So that will, with respect to that, I will tell this is my coordinates. This CG point will tell that where I am. Okay. Now whether it is like this or like this or like this. So that will tell another 3 axes of rotations are there. So one is X, Y, Z and angle, psi, phi, theta will call. That means rotation. So these are all the 6 degrees of freedom what I am having. I can move like this X, Y, Z direction, or I can rotate about all 3 axes. So if you know all these three, that what is the NGC, earlier we are telling na NGC. NGC means, N means navigation. Navigation means what it tells is where you are in terms of position and in terms of orientation. So first you should know where you are. Then G stands for guidance. So guidance, what it does, you want to go from this point to the designated point, how we can go. Whether I can go like this, suppose I want to reach that corner. I'm having a multiple paths. I can go this one and go like this, or I can go this one, that. So which is the best path? If you are guidance, you are telling that what is your objective function, whether I want to go in a less time or I want to do the less effort. So that tells the guidance. So navigation tells where you are, and guidance will tell how to go from the designated point to the destination point. So control job is just to follow the guidance instructions. So these three, if you are perfect, then this landing is a simple problem. So here lunar mission, what is another advantage or disadvantage you can take? Here there is no atmosphere. Nothing is there. It is like all your Newton's laws of motion, you can straight away you can apply. There is no aerodynamic forces, all this drag, all those things are not there. So all your F equal to ma equations, everything you can apply nicely, you can solve all your kinematic equations, everything you can use it. So same thing we also applied the thing. But only thing is other disadvantage because there is no atmosphere. So here this is the landing means what object is moving with a particular velocity. I have to reduce the velocity. Then only I can come and smoothly land it. So this reduction will happen by firing the engines. So that means engines means I need some propellant. So I have to carry how much is the velocity I want to kill, that much propellant I have to carry. If there is atmosphere like Mars and all, I can use a parachute where I can reduce the propellant requirement. So both way advantage and disadvantage is there. Sorry, I will go back to this. Previous slide. PDF also you can open, that is also there. Okay, that was when I am telling that navigation point, what all the sensors I want to tell that where I am, some sensors are required. What sensor to tell the position? I need a one position sensor. So one is for height purpose, we add a altimeter. And for position, I have to depend on camera based position. Otherwise, here we are using the GPS to get the XYZ with respect to the your location precisely you can tell in XYZ with the GPS. Their GPS, nothing is there. So I have to depend on sensor. One is altimeter I can use. I will tell what all the sensors we use. And similarly, I am going at what velocity I am going. So for that time Chandrayaan 2 time frame, we don't have any 3-axis information to 3-axis velocity. What is this velocity, vertical velocity, all 3 dimensions. I should know, then only I can control the craft to reach the designated point. So that was the roundabout way we used a camera based sensor, vision based sensor to get the velocities. And after this Chandrayaan 3 time, we felt that yes, this is the velocity sensor very much is required. So ISRO developed the LDV, laser-based Doppler velocity meter is. This was the one new element is introduced to get the navigation information. Then similarly, the propulsion system also, some improvements are done to get the. So this is the propulsion system. What I am telling is, when the module is going, we are applying the opposite thrust. So how much thrust we have to apply? These are all the not like a continuously firing the thrusters. It is like a your bike accelerators are there, na? So these are all throttleable engines. That means whenever I want to go or apply brake fast, I want to apply the more thrust, or slowly I want to less thrust, or I want to just maintain this one, just to balance the gravity. So these are, that's why the engines are throttleable engines. So not a fixed thrust engines, we require throttleable engines. So that throttleable engines also, the throttling capacity also got improved. How to precisely to make a velocities less, that throttleable engines, that improvement was done. Then in another one, Chandrayaan 2 time, we are having only one path. I want to go to here. If I am not able to go there, what to do? There should be alternate. Na? See, suppose we cannot tell that everything we can go right. Even if it is wrong or if it is not able to reach, what is other alternative? So some of the paths here we have put the whatever the maximum possibilities. Where and all it can go wrong and how to correct it. All this multi-path handling also, failures also we incorporated to improve the robustness of the system. So that means any failures or any unforeseen situations, how the system can safely land to the designated point. So after that, what we did is the testing condition. Testing Chandrayaan 2 to Chandrayaan 3 also, we did a lot of improvement in the testing. So someone was asked, I think, that how this rover was tested, or whether the environment conditions are. So when that testing is a very, very important thing. So that generally what anyone will tell, test as you fly, fly as you tested. That is a fundamental thing you have to follow. So when we are doing all the tests, we are seeing that what type of terrain and what type of environment and what are the velocities it is supposed to experience the correct information or not. So that is a must. So that testing and all done. So Chandrayaan 2 to Chandrayaan 3, if you see the mission profile, from there I will explain what are the test cases. Generally, we are seeing the cold test, integrated cold test, and integrated hot test. Cold test means don't think that it is like a freezing temperature. It is not. So our terminology, cold means there is no engine firing. That means we are not using any engines. Only we are seeing the sensors performance. I told now navigation performance. So in this navigation, one basic sensor what we are using is the inertial navigation system. It comprises of 3-axis accelerometer. Accelerometer will give your delta velocity or your delta position, and gyroscope. Gyroscope will give what is your rotations about all axes. 3 axes are there. 3 axis gyroscopes if you put, you will get what is the rotation. And keep integrating, you will get the continuous, how many degrees it has rotated about that axis. Similarly, accelerometer will give the delta velocity. That means delta velocity by delta time is your acceleration, and integrate it, you will get a velocity, another integration, you will get a position. So like that, you will get that is the inertial sensor what we are, any flying object or any thing it will use, that is a basic sensor, is a INS, inertial navigation system. But the inherent problems what we are having is the gyro is having its own drifting. That means even though if you place here and it is not rotating, after some time if you see the sensor data, it will tell that you are rotated by this much. Gravity of the your moon environment means what is the moon gravity, that doesn't know. The sensor cannot measure the gravitational force. It measures only the specific force. If you are keeping here, it will measure 9.8 G. That means you are thinking that it is measuring the gravity. No, it is measuring the force applied by this table. So that is always it will measure the specific force. So that means I want to propagate from the sensor data. If I am keeping this object is a lander or any object is here. Now I want to tell after 10 minutes, I want to tell that where this is. It is not moved. But if I see the accelerometer data, it is seeing the 9.8 meter per second square acceleration is there. If I integrate, it will tell that you have moved away. But what I have to do is, I should know what is the acceleration due to gravity, that has to subtract it. So when you am doing the navigation algorithm, we should know what is the lunar gravity. If I am doing a lunar navigation, lunar gravity at that point, you have to subtract. Then only you will get the precise position and velocities. So this ICT, what we did, all the tests are done in a ground environment. And what are the velocities the sensor can do, and what is my mission profile. And this is I am going to what velocity I am going to travel, what all the phases I am having, whether these sensors are giving the correct data or not. So, but the velocities, if you see, it is a very high velocity, 1.68 kilometer per second. So that is none of the object in Earth environment. It is not possible to demonstrate. So now we are breaking down the problem into the small things where I can test it. So if you see the Chandrayaan 2, what are the half of the trajectory we have already demonstrated, and we are having a good experience and good hold on the navigation, how it will. Now the basic thing what we are in, when the sensors are, I am doing the hovering. Hovering means it is not moving like this. Our nomenclature is hovering means I am stationary at one point. So that platform is stable and the sensors can give the proper data. So how to do this one at a, if you see the trajectory, we may have at a 2 kilometer or 3 kilometer height. So that is, we took a helicopter, and in the helicopter, all these sensors are mounted, and the helicopter is flown the way the trajectory is designed. So what is the velocities it is going to experience on orbit? The same test conditions we have tested on this. So that will give the good confidence. Yes, it is going to work. So I have matched the velocities and what is the rotations it is going to experience. But what about the environment? Here it is a 1G condition is there. So propagation, I have to put the, for ground propagation, I should have a one more reference unit. With that, we have compared. Yes, these sensors are coming correct. Now, other condition, what is the atmosphere condition is there. So what is the moon case? Atmosphere is not there. What are the laser based some sensors are there. Those performance also assessment was done. So how it was supposed to give in Earth environment and predictions was there, whether it is matching with the test data. So this is the new test setup we took in Chandrayaan-3, where it has given the sensors has given the perfect results, and what it has not given any observations are there. Those things are corrected. Now we got the perfect sensor data and sensors are working conditions. So that way we are fully confident that yes, sensors are working perfectly. Now, and it is done not like a individual sensor. So in this cold test, we have tested like a end-to-end. So navigation solution, I am initialized here and I took the helicopter from the different trajectory and I have come. So full end-to-end with the sensor data taking and the navigation algorithm verification until end results. So it is not like a only sensor data, it is a full, like a flight software, fully got tested. The navigation portion is fully validated. So that way it gives the confidence that yes, this is a navigation system is perfectly working. So that way we have cleared that navigation system. Now similarly, this in loop. See, when I am doing the hovering, I have to balance the with respect to ground. So this also we demonstrated in the scale down model. Scale down model we took because this is a 700 kg we cannot lift, and these engines are this atmospheric engine will be different. We may not get the what thrust is 800 Newton thrust is giving. It may not give you the same engine if you use here. It may not. So now minimum systems with minimum systems we made a one engineering model or which is going to give the IHD model. There all the required sensors and propulsion system was mounted, and we demonstrated yes, I am wherever I want to. In the mission phase, what we are in some phase, we want to hover it. Particular height, I want to hover it. If we tested in Shore only. Shore, we erected an 80-meter tower is there. From there, the physical module is hang, and we controlled with the RCS for the attitude control and the engines to descent and ascent. We demonstrated. So that is the end-to-end. That means the sensors will give, INS sensors will give where you are, how you are, what directions, everything was there. So control and guidance system is well tested. So it also gives the confidence. So NG system, navigation, guidance and control is fully tested. So that gave the, for Chandrayaan 3, good confidence on ground itself. Yes, it is going to be perfect this time. So these are all the improvements. All the already I has covered. Now this also is covered. See, this is the finally what is the same we are going to repeat the Chandrayaan 2, but the orbiter is already it is there and it has done the it was working. So again, repeating the same payload, we felt it is not required. Now I want to improve the lander system. So lander system improvement means what? I have to add the extra sensors, extra propellant, extra this one robustness. That means extra propellant is required. I want to carry this one. So, but the liftoff capability of the launch vehicle is limited. So what I can do it? I can reduce in the propulsion module. So propulsion module this time what we made is only just to carry the lander module to and drop you in the lunar orbit. So if you see this, all these earthbound orbit and lunar orbits all done by the propulsion module, and it is separated at 100 by 100 kilometer circular orbit. From there, the lander will take over and it will do the job. So why we took these many orbits? Sometimes the advantage is there. It is other agencies will landing. It will take a very less time. And by doing this one, what advantage what we are giving? See, what all tests we have done, and what are the alignments and calibrations on orbit, we are getting the opportunity to calibrate and get the any corrections are there, we are going to do the corrections on orbit. Whatever is grounded tested on orbit will be slightly deviations will be there. There we got the opportunity to assess the performance of all the sensors and all the systems before starting our descent. So this one only I am telling that axis yaw roll pitch. You can this is the orthogonal we are generally defining the coordinate system. So here what we are calling is roll is the vertical, and this axis which is rover is closing that. This is we are calling as a negative yaw axis, and the right-handed system completes the third pitch axis, yaw roll pitch. If I am rotating about this axis, that means right hand system like this. If you are rotating, that is a positive roll motion. And similarly, you put the thumb indicating the direction of your axis, and this tells the rotation. That is a positive convention we are using. And this is the total integrated module and a rover. Now, if you see the sensors, what all is there, I will just to show that what all the elements are there for the NGC to support the NGC. So we are having a main 4 engines are there, 4 throttleable engines for the braking purpose. And this is the LDV to give the 3-axis velocity information. And this is the altimeter, LASA. The laser-based altimeter, it will fire the laser and see how much flight time it takes, and with that calculates what is the range. It's a range only it will see, slant range it will do. And one more is there, K-band altimeter, K-band radio altimeter. So that will the RF-based system. So we are having 2 different concepts for the altitude, so that the redundancy and one system is not working in that environment, other system will complement. So maximum we tried the 2 different technologies, so that the redundancy point of view, it will be very much advantage. Otherwise, if it's the same technology if you use, if it is failing in that environment, the chances are for the other system to fail. So here the velocity is having a laser based, and along with that one we are having a camera based, vision based sensor to get the velocity, but it gives the only the planar. If I am taking the image, 2 images, if I am seeing what it will give, it will give the in this only it will give the what is the velocity in the image plane. But I want to get the what about the velocities about 3-axis information. So accordingly we have to transfer to the what is the image plane to the sensor axis. This is the air roll pitch axis I told. No? So those velocities, the transformations, any corresponding math, everything will be added. So similarly, one more, after reaching the end conditions, if you are seeing the nicely we are reached there. But the moment you reach there, you are seeing that like this, one crater is there, or one small undulation is there. I cannot put one leg here, one leg there. So last moment, we want to see the correction. How much correction is capable and where to do it. So we decided at 150 meter, we'll do the corrections, take the hazard map images. If he is telling that, yes, wherever you are there, you are safe. then you land it. So that is another sensor is used. The actuators, what we are using is, I told you that these are all the main engines. These are all the small, we will call as a RCS, reaction control system for the, to maintain the attitude. Attitude means orientations. To maintain the module vertical, or I want to tilt it, you rotate it like this. Suppose I want to go from here to there. What we are doing, the engines are firing in this direction. Engines are always balancing, or you are always in the downward thrust it is giving. So I want to move this one. We don't have any horizontal engines to move laterally. So what we are doing with these small engines are there, no? These small RCS. You just give the firing, it tilts like this. I'm giving you rotate by 5 degrees or 2 degrees, correspondingly how much distance I want. The moment it is there, one component is a gravity balancing, other component is horizontal push. And after reaching there, I will make it this. So like that, we achieved the horizontal movement also. And this is the one more type of the actuators. This will call the flywheel. Inside, if you see, this is the inside the flywheel, like our reaction control system. How it works? This is a satellite or a lander is there. Over that, we have mounted one more, the reaction wheel system. That means inside one flywheel is there. The moment it rotates clockwise direction, it will give the opposite angular momentum, opposite direction. So that is here we are firing the chemical propellant, and here it is nothing, is by modulating the speed of the reaction wheel, I can get whatever the rotation we want. Here we are not spending any propellant. But the moment you want to use these engines, we have to spend the propellant. So only for attitude control, when after separating from the propulsion module, to assess all the sensors, we have to be there in the orbit for the 3-4 days. So in that, we don't want to spend fuel, but because we want to reserve that one for the landing point. So that's why we have put, even though these are all, we used these 4 reaction wheels. Minimum 3 is required. If you are orthogonal, if you are putting 3 axes, you want to rotate, 3 wheels you put, it is sufficient. But redundancy we want. Suppose in case any wheel failure, what we can do? The 3rd axis cannot be done. So for that, what is the best configuration? So you put the tetrahedral. So each wheel is giving the 3-axis torque. So any wheel is failed, I can control the 3-axis information. So everywhere, if you see our design wise, all space systems will have a redundancy and the failure modes. That is when we are designing, definitely those things we are thinking. Otherwise, the normal design, if you put the failures, if you are not able to handle, then your system is failing. So these 2 are the star sensors, which will give the absolute attitude where you are in space. If you are telling that, yes, I am there. Now you from coordinate system, you can measure. But this is star sensor with respect to star catalog, will tell that in the space where you are in terms of orientation. So these are the configuration for the actuator and sensors. And this is the power descent trajectory. It is more similar to the Chandrayaan 2. We are not modified much because it was well thought and it was meeting our requirements. So most of the thing is, it is in orbit phase. It is in 100/30. If you continue, you will be 100/30 kilometer orbit. Here we are having purely the horizontal velocity, and there is no vertical velocity. And we are at 30 kilometer site, and our landing site is something around 745 kilometer away from the landing site. So here we started with 4 engines. The maximum horizontal velocity is killed. So simple thing, what you can do, you kill the module is going like this. It is going like this. You kill the full velocity, full horizontal velocity. What will it become? Then from there it will drop. So wherever you are able to kill, and it will drop. So somewhere we want to optimize the propellant, and some guidance algorithms we checked, and it is a parabolic descent is giving the best optimal solutions. See, first we came up to this phase, what we are almost 7.4 kilometer, we are calling the rub braking, where the most of the horizontal velocity was killed. And in this phase, next we started attitude hold phase. Attitude hold phase means we are maintaining the orientation. Till in the rub braking, we are continuously, we are steering. This is the thrusting direction is coming. The module is coming, slowly steering like this. And attitude hold phase, we maintain like this. This is because we want to see the altimeters, where we are bringing the altimeters in this attitude hold phase, and see that whether I am corrections we have to do, because our INS is started here. Inertial navigation system is started here, and I have spent 690 seconds, and it would have drifted you. It will tell that even though you are reached 7.4 kilometer, ideally, the inertial navigation system would have told you are at 10 kilometer or different point, based on the what type of errors it is having. System is having errors. To correct that one, we have to depend on absolute sensor. So absolute sensors, where to bring? See, I can bring the sensors right from the starting onwards, the absolute sensors. The constraints, we have to see that whether the sensors are available or sensor can work, or INS is not diverging, why to correct it. And altimeter, what it is doing, it is suppose laser you are taking, it will hitting the laser beam here and getting the height information. If you see the actual lunar terrain, there it is a lot of undulations are there. That means if you are following this from here onwards, the absolute sensor, what would have happened? The trajectory will be doing up and down. That means you are matching the terrain. So precisely it is not required, because I want to come to the, our intention is here we have to do the correction. Here any undulations are there, it is of not much concern. So that's why we are bringing in a particular place where it is really required to correct the INS navigation. So here the sensors, what altimeters we brought into loop to correct the altitude errors into the INS navigation. So after this, after one update, we came to know where we are. Suppose I am here or here, where with respect to I targeted 6.8 kilometer. After getting the update, I know where I am. So from there, I am controlling to the 800 meter. So I'll bring the module to the 800 meter, where my target velocities are 0. That means almost I am reaching the above the landing site, with all the velocities are killed. Now we started with the 4 engines. Now 4 engines are not required here, because the module already we have spent the propellant, the mass of the module is reduced. If I use the 4 engines, it would, again, the thrust is more than the gravity, it will fly out. So I have to, 2 engines are put off here. So with the 2 engines, we started coming down. So vertically, now because I am already above the landing site, any corrections are there, we are going to do the correspondingly how much to be horizontal move. So in Chandrayaan 2, it was a precise landing, and Chandrayaan 3, wherever you are there, because we have a very bigger landing area of 4 by 2.5 kilometer. We are with all the ground studies, we felt that it is not going away from these boundaries. So wherever I reached within the 4 by 2.5 kilometer, it is a safe. So I need not do the any corrections, so that I can save the propellant. So wherever I am there, from there we are coming the vertically. While coming, we are taking the periodically, we are correcting the INS navigation. Once we are here, this you are not traveling more ground downrange. So that means all your sensors are seeing the same locations. So it will keep correcting your INS errors. So now, but if, in this process, if you are having a year one boulders are there, then it is not safe. Not safe to land directly. So particular height we want to do again to do the correction, whether I am reaching the safe point or not. So whatever the hazard detection camera we brought in around 150 meter, depends on this working range and accuracy. 150 is the good place we have placed there. At 150 meter, it will see the ahead of this one, the terrain. It will take the snap of the terrain, what it is there, and it will compare with already we are having the maps on board. It will check whether it is safe or not. If it is matching is there, then it will check back. Even though this place itself is safe. Suppose wherever I am there, I am safe only. But why to travel that 150 meter or whatever the new place? So what is the algorithm also we ask this, wherever you are seeing the image, you propagate back and check whether really the vertically down it is safe or not. So exactly in the Chandrayaan 3 in the flight also, we saw the hazard map as given. Yes, you can go vertically down where already you are in a safe position. So we didn't do opportunity, we didn't do this 150 meter travel. That was not called in the actual flight. But that one only we also decided, based on simulation, we also felt that mostly this mission is going to be vertical descent. The same way it also happened. Then once it is told that, then from here onwards, we are slowly correcting the one. And after coming to the 10 meter, we are coming with the constant velocity where the legs can take care of the load. So 1 meter per second, we started coming. So in the different phases, from here onwards, we are having altimeter information, the LDV velocity information, along with the INS propagation. And this attitude orientation is set by the star sensor before power descent start. Further, we are not updating the any attitude information. So attitude is because the INS system is the gyros are very perfect. This and it is there is no drift. So the orientation wise, that's why we see that is exactly the vertically. It is not made any error in the orientation. So this already in technologies, whatever sensors were developed for the landing mission, I told already. The hazard detection camera for the safe side. Okay, this also reaction control system, the small thrusters, what is the capacity? 58 Newton thrusters, so 8 numbers we used. So this is the simple way with the NGC block diagram. This is a total system, how our navigation guidance control system is working. So I don't know how much time is there. Huh? So this is the actual system, what we are to do the simulations. I should know the system dynamics. So this is what I am telling is, this is actually on board is a lander is there. But here when I want to do simulation and check whether my lander or whatever my algorithms are going to work properly. So this is, I want to model it as a mathematical equations. So all these differential equations, Newton's laws, Euler's motions are used here to mimic the motion of 6 degrees of motion of lander module, and it will give the gyros and accelerometer. These are also models are used on orbit. Actually, the sensors will be there, and ground simulation will be the mimicking the all the sensors, the way it is behaving the lunar environment. We are going to model it. We model all these things, and the guidance algorithm to reach the different endpoints. The navigation is telling that where we are, and guidance is telling targets we loaded. So these two informations, it will generate the what is your orientation along with the what should be the your force or acceleration to reach the point. So those two things, one will go to the attitude orientation for attitude control, where we are using the reaction force, reaction control system. For the force, that means to apply the acceleration, we are giving to the engines, where the bigger engines, 800 Newton engines, to get the acceleration. So smaller thruster we used for the attitude correction, and bigger one used for the braking power. So these are the simple way, the mathematical equation. You can take torque equal to I omega dot. And this will tell the rotational dynamics. This is the translation dynamics, F equal to ma. The simple way. And how the engines are, the moment if you give command, how the engine is performs. It may not be like ideal. If you give the command, immediately you may not get the thrust. It takes, the system takes its own delay and response time. So all these things are modeled to match the exactly the how it is going to behave the during the actual descent. So these are all the mathematical model for the sensors, where we match the prediction versus what are all the, this is the loss output, prediction versus our models versus actual test data. If you see, there is no deviation. That means our models are exactly mimicking the actual sensor. So I can depend on my software and my simulations to do the n number of test conditions, whether it will do successful landing or not. So these are all matched with the cold test data. See, this is the Kara data versus what is the model. So after that, one more doubt what we got is, yes, it is once it is landed, what will happen? It will bounce back because I am coming with some velocity. What will happen? What type of upward force it will give? So those are all things we are not able to, because different joints, it is not taking directly the vertical load. It will having some cushioning also. All when it is landed, it will having some observers. So those type of dynamics we are not able to exactly simulate. So what we took the stand is, yes, we are having this is the model. It is totally, it is Adams model is there. The mechanism systems with all these joints, it is there. So what we integrated with this model, the Adams model, to our simulation. So simulation is taking the sensor data, what reaction forces are coming, then integrate it and see that where the system is able to stable, it can withstand. And in a slopey environment, or it is having with a larger velocity, whether it will topple, all those simulations we did in an integrated fashion, along with the Adams and our MATLAB simulation. Now this is a navigation, already I think I explained. So inertial navigation, it is taking the LIRAP, that is a incremental angle, incremental velocity. And the gravity it is not sensing. So we have to use the gravity model to get the what is the position and velocity. And along with the aided sensors, we are having a altimeters, LASA, Kara, the LDV, Doppler velocity meter. And each sensors are giving in the sensor data. And we are fusing this sensor data and giving the navigation input to the guidance. And similarly, in the local, when we are coming to close proximity, we are using the velocity sensors also in loop. Now problem what generally it will give means sensors, whatever sensors are there, what all you have to consider is sensor may not give the all sensors. Some 4 or 5 sensors are there, all may not give the simultaneously the data. So altimeter is giving one time, the velocity is giving some other time. So you have to correct for the latency. That means you got the sensor data that may be older by 500 milliseconds. That means already you crossed, your velocities are changed, but it is telling that the 500 milliseconds back you are having that velocity. Now I have to do the actuation corresponding to the current time. So what we have to do is, whatever the velocities are there for the past data, we have to correct it to the using the accelerometer data, which is having 8 milliseconds, to bring it to the current time and do the guidance. So these are all the real time, those are all the challenges where if you are using these asynchronous systems. Okay, this is a guidance. Already we told guidance is giving the what is the acceleration is required to reach one point to the other point. What is the guidance is required, whether it can be polynomial guidance or it is a PV guidance. What finally it gives this is the acceleration. I know the object is here. I want to go to that point. What should be? I should impart the acceleration. That is a simple thing is giving. So acceleration, if I know acceleration vector quantity here. So vector quantity magnitude is given to the what should be the force, translate to force. I know the mass of the module, acceleration, and find the force. That force you give it to the engine. And the vector quantity. This is a normalized vector. This is a vector quantity will give the direction. So direction quantity you give it to the attitude control. So your desired acceleration direction will be achieved. And this is the control system. Control system, what is it? Here we got the what is the reference attitude. That means what is the orientation. So control system, what is this is my reference. So simply try to maintain this reference. What is the given reference? You see the any error is there, you make the error 0 with respect to this reference. What is the orientation it is asking? If it is like this. It is asking to do this one. You make the module also. This is the initial, this is the design. So these are all while designing, we'll do the single axis design only. So some of the extra, see, these are all what we told is normal operations. Now the people will ask, no, if it is having a problem, you are not able to reach the designated point. What are the safety precautions we are taking? So suppose engines are, or it is not able to develop the thrust. Some of the safety features also important. We introduced a real-time retargeting, salvage also in case of very low thrust is coming and module is falling, and what to take. Or suppose in case the guidance is asking to do the tumbling, that also we want to take care of, avoid the tumbling. And engines are some cases 800 is a maximum. If it is asking demanding more or demanding very low, so there also some protections are we have to put. Apart from the actual design, these are all the safety measures are also introduced. Then similarly, if engine is not able to perform the delta or braking action, because the reaction control system is there, you can augment with the RCS also. So that these are all the extra precautionary safety measures are added in the NGC system. So once all the system is designed, our next job is to develop the software and put it in onboard processor where it can do the real time. There is no human intervention. Once the power descent is started, there is no ground command. So all the things, how to go, all the milestones I told, when to come the sensor, what to do, how to validate the sensor. When the rejection, any wrong data is coming, what to do, when to orient, when to change over to one phase to other phase. All those things are programmed in a meticulous way, and it is very thoroughly tested, each and every path of this one. This almost the code is more than 1 lakh lines of code. Each and every line was very tested, well tested. All parts of the software modules are tested. So we used different test cases like a 6-job simulation test bed where it is a purely the software simulation, where it is a only mathematical models are there. And we are having a software in simulation. That means what is the flight software? Flight software with all the other modules as a software modules also we tested. And I told the hardware, the IHT and cold test also we did, and drop test to see the leg mechanism, whether it can withstand or not. This is the hardware simulator where we have put all the sensors and actuator is a total loop. NGC loop is tested with the actual hardware, actual interface, so that there won't be any communication between the sensors, whether data missing, those protocols also the well tested. So that way the different test cases, that means whether I have to test for the nominal case or it is a failure case or beyond the failure, beyond the capability, that also tested. What is the one guideline? What we are saying is any test case, system can fail, but software should not fail. That was the one general guideline it is giving. It may be, you may be, we can test that any mad case, whether it is any test case, like 2 engines are off, what will happen? It should do what way you design the software. But then software should not give any problem. Those type of bugs also, some mad type of simulations also we did. So that way you see that we are seeing that what is the expected, this is the error ellipse. What we are seeing that given the designated point, we are, if all sensors are behaving a 3 sigma, what is the design value will be here. Otherwise, my error ellipse will be increased. So that way from the ground simulations and with all the confidence, we could tell that yes, everything, each and every parameters, like in terms of propellant and in terms of touchdown velocities, all we analyzed that yes, it is, these are all design parameters are well within the specifications and it is cleared for the landing also. So these are all the various images where we have tested our algorithms and systems. Once anyway launch comes, launch activities, launch issues, what to do real time, it is like a 30 to 40 days of continuous effort where the people are day and night they spend and they see that each and every data, whether observations are there or it is go no go. So that way we have cleared all the parameters, and we are having a hardware simulators also. Each and every activities were well tested before uplinking to the command to the system. So this is, if you see the bounds wise, see what we predicted and what is achieved. See, this is the black is the prediction and blue is the actual flight data and within the bounds. See, that much accuracy and that much is the capabilities what we got in the Chandrayaan 3. So that's all from my side. So thank you. Thank you from
Thank you, sir. Audible, right? Thank you, sir. Thank you very much for a wonderful talk. And I learned so much of technology, science, mathematics, simulation, so many things involved in this thing. When during the landing, we were watching the video, with live things that it is slowly landing, and behind that, so much of things is there. Thanks for explaining all these technologies in details once again. Now I request our Professor Shishidhar Guma, Dean International Affairs, to hand over the memento. Next one. Okay, so in the morning session, we started from the overview of Moon Mission, Chandrayaan 3, and then Aditya L1. And then we started with the how control systems. And now let's have a talk on the ground systems for successful planetary and lunar missions. We have Srinath, our speaker, Srinath Ratnakumar. And let me introduce Srinath Ratnakumar holds master's degree in physics from Bangalore University with 6 gold medals and UGC net certificate. Later, he joined as a scientist in ISRO and worked for Chandrayaan 1 project for the establishment of new facility at Byalalu near Bengaluru. The campus is Indian Deep Space Network led agency of ISRO for all planetary mission tracking, command and control. He has played a major role in data ingest, process, archive, and dissemination of Chandrayaan 1, Chandrayaan 2, Mars orbital mission. And currently, he is working on the data archive preparation for the ongoing astronaut ground system for payload configuration, data reception, and processing in Indian space science data systems for payload configuration. He has been identified as a facilitator for human rating certificate of the ground systems for a future Gaganyaan mission. He is working for Indo-French mission Trishna. He has played a key role in Chandrayaan 3 mission in handling of data and the member of rover path planning. He was member of many ground segment committees of Chandrayaan 3 lander and rover and played active role in this mission. He is interested in communicating the benefits of science and technology to the public, and he holds a public outreach group called Creative Team for innovative talks covering non-textual, non-syllabus, and non-academic knowledge. And he has also worked as an advisor for Dr. H.N. Sub Regional Science Center, and also is a founder member of Karnataka Physics Association, and he edited 3 books in Kannada as a part of ISTREAC Rajyotsava. Thank you. Thank you, sir. Thanks, sir.
Check. Andariki namaskaram. Good afternoon to all. and good day to one and all, my senior colleagues, Shankar, Shrikant, and Bharat. I think I don't want to stop you in between the lunch and this boring talk, because whenever you say ground segment, we were be the last in the mission, like Shrikant will say. But Shrikant depends on us for his spacecraft mission operation. Anyhow, post lunch you will have a fantastic what you call solar physics talk by Shankar. Somehow it's always important to know some of the services or a support from the beginning of the conceptualization of any space mission. When you say a space mission, you have three important components. One is a space segment, we call it as a satellite or a spacecraft. The other thing is the carrying vehicle, which we call it as a launch vehicle. Then both launch vehicle as well as the spacecraft has to be controlled or monitored or operated from a particular ground. That is the area where I represent. It is not the, disclaimer I'm trying to tell, it is not the whole one-man work. It is many people have worked in establishment of the ground segment, which I will be trying to cover here. I represent ISRO Telemetry Tracking Command Network, which is situated in Bengaluru, has a headquarter. We are part of ISRO, but we have many centers across the globe. It is because of the nature of the spacecraft. So let me directly go into the saga of the ground systems for successful planetary and lunar mission of Indian space program. In between, I have also included few other missions where the ground segment plays an important role. If you look back, let's say, go back to some 40 years back, what was the condition of space program in India? If you look at it, we have to be indebted to the great man, Dr. Vikram Sarabhai, who started. Our ground system also started way back in this particular area where we call it as Tumba. Most of you, if you are not aware, Tumba Equatorial Launching Station, TERLS. Even today, it is successfully being operated. One more extension also has come into Sriharikota. So that is the first place where ground system operation started. Nike Apache rocket from the United States was brought by Vikram Sarabhai to study there on atmospheric. So that is the origin of telemetry in India. First telemetry started from there. So this is the place. Small story is there. Hope you may be knowing. This is a church, Mary Magdalene Church. Vikram goes there and asks the father of the church that I need this church. Can anyone give the church directly like that? They have given. This is the fabric of the India where they promoted space industry. Today, the church is a museum, and lot of ground systems were designed, developed in that church by, you may be seeing Abdul Kalam sitting there and filling small rockets, all those photographs in that church. It's a sleepy fishing hamlet called Tumba. And this is the first rocket picture. Even today, every month, I think 4th Wednesday, I think it is one sounding rocket launch happens there. People can go, students can go there and see, and the scientific community researchers can propose instrumentation for the sounding rocket also. So if you look at here, if we have to play a meaningful role nationally and in the community of nations, we must be second to the none. Please understand, application of advanced technologies to the problems of man and society. This was the original vision coined by Vikram Sarabhai. If you go to ISRO website now, the vision is now modified. This is I have not taken the full vision. I have taken a little bit of that one or two points. Harness, sustain, and augment space technology for national development. We have retained that, whatever is told. But the extra added is science research and planetary exploration. If you look at the first satellite, Aryabhatta, we started with science research only. But if you, in the country like India during the 40s, if you say that I want to launch rocket, satellite, people have scolded us. You are wasting money in the name of research. Then, Vikram Sarabhai has convinced the government at that time that it is going to be useful. That's what in the previous talk, I think Ritesh was mentioning about the television experiment, satellite instructional television experiments. That's how we could convince the policy makers that space is important. Now we are more into this particular one, science research and planetary exploration. And the new dimension which is added, the recent space reforms, is promote and authorize private firms to play a key role in the global space market. This I wanted to bring because a lot of interest is there. Those who pass out from IITs, you can start your startup business. Yeah, this is how the where all the space, it's a government setup now, whatever I'm showing here, ISRO, where all it is situated. It is there from Jammu Kashmir to till Kanyakumari, we have spread out, but still you need a lot of regional and national balancing. That's the reason we are coming up with space startups. This is on information. I mean, this is the place where we belong. You can see here, Bailalu is there. When we say ground segment, there is one more important ground segment also, Hassan, which I will not be covering. We can have a discussion on that. I will be only covering on the ISRO's low Earth orbiting satellites ground segment, as well as the planetary and lunar science segment. So this particular slide indicates that India is self-reliant in rocket system. But for me, ISTRAC, why it is important is, depending upon the nature of the satellite, my ground trajectory will, like the ground trajectory of the launch vehicle will differ. When ground trajectory differs, I have to have a ground systems there to support that one. So if I am launching PSLV, if I am launching a GSLV, or if I am launching SSLV, what is the ground trajectory? Where all I need to build my ground systems? Why do I need a ground systems there? I have to monitor in terms of receiving telemetry from the rocket. First portion is rocket, second portion is on satellite. So I have to receive telemetry. During the launch, it is only one way. You don't do any commanding to the, except abort type of operations. It is only listening to the telemetry from the launch vehicle, whether it is a PSLV, GSLV, or SSLV. When it comes to the spacecraft, it's a two-way. You have telemetry, telecommand, ranging, all those operations. For this type of application, these are the requirements from the Shrikant's team, mission team. They said that we need all these type of things. So accordingly, ground systems have to be built. Yeah. Apart from that regular launch vehicle, this is a new dimension which is added, a challenge to the ground system. What is this experiment? I'm just trying to give you the different requirements posed by the launch vehicles for a ground system. So this is RLV, reusable launch vehicle system. Launch the rocket with a unmanned aerial vehicle, and that aerial vehicle has to land it. And you have to control, receive the telemetry. Again, here it is one side. There is no telecommand business. So that also another new challenge which we have completed in Chitradurga. I will show you those things also. Yeah, this is the recent challenge which is posed by the new, what you call, demonstration of a new technology towards the Gaganyaan. Hope you have seen all this test vehicle of the Gaganyaan vehicle. Here also, a different challenge is posed on a ground system. Whatever conventional ground systems I am having may not be sufficient. I'm trying to give you the requirements and challenges posed by the launch vehicle system on a ground system, how to configure or design your. So this is the overall the evolution of the launch vehicle system. I think we are somewhere here at this particular stage. You have a lot of evolution. In future, you have a great future. I mean, once you come out of IITs, you can also contribute in establishing the new technologies in terms of ground systems for tracking, telemetry, commanding, and network. Similarly, once, like I said, for us, the dictation is given by the launch vehicles as well as the satellites. Then what are the different requirements and the challenges posed by the satellites? It starts from the good old days of Aryabhatta to till the Mars mission of 2013 and the recent mission of Chandrayaan-3 lander, which you have heard both Bharat and Shrikant, and also the new technology which we are going to demonstrate, Gaganyaan. What are the satellite related, what you call the challenge or a requirement posed? It depends basically on the nature of the orbits. What type of orbits? Hope most of you are familiar. Those who are not familiar, it will be helpful. When we say low Earth orbiting satellites, less than 1,000 kilometers approximately, then you have a medium Earth orbit, which Russians, they have most. We have many low Earth orbiting okay. Then you have a geostationary. We have both, first one and second. We don't have many, like we are not working, this is only for Russians. Same way, equatorial satellites, polar satellites. When I say the orbit, please draw a ground trace on that. That means the satellite is moving in the sky, but on the ground where the trajectory is there all I need my telemetry or telecommand monitoring stations. That's the reason I'm bringing it to the notice. And there is a new segment GPS, which we are also into it, NAVIC. So what are all the different, now next thing is, one is rocket, another is a satellite thing. Then the application of satellite also poses different challenges for the STEM. Because in Chandrayaan-3, one is launching Chandrayaan-3 in GSLV, then reaching to the moon. After reaching to the moon, rover has to work, lander has to work, and they have to transmit the ground payload data. So collection of the data, or we call instrument data, that also poses different type of challenges to design your ground system. Same way, stereo imaging if you are doing, or the different, like see from Bhaskara and Aryabhatta days to till now, we have gone to 0.3. This is in terms of Earth observation, I'm telling. So when you go for a higher resolutions of a target Earth, or even a moon or a Mars, data rates are high. When data rates are high, different challenges will be there. You have to transmit the data. So then my ground station design and specification also will differ. That's what I'm trying to convey here in this slide. Depending on the objective of your satellites, the type of instruments or payloads which you are hosting on the satellite, and how data has to come, whether you want to data, see in Aditya, you will listen that every 10 hours, every half an hour data will come. Whereas some satellite every day, one time only data will be given. So this is called data collection wise. One is telemetry, telecommand, ranging. Other one is payload data reception from the spacecraft. These are the what we call requirements or the challenges posed by the both launch vehicle, spacecraft, and the ground system. Sometimes there are certain experiments also. Like landing is one experiment. Reaching the moon and revolving is one experiment. Whereas landing experiment, the challenges of having a continuous communication, and suppose if you have landed on a backside, what Srikanth has explained is, front side you have landed and you have a good communication. Whereas Chinese have landed on the backside. Then what should be my ground? Can I have a ground station behind the moon somewhere? No, you have to think. You cannot say no. There may be possible. So that's how, whether you call that as a ground station or a relay satellite. So that direction, your experiment also matters. Now you are going to Lagrangian 1 point. That is also reaching to the Lagrangian 1 point is an experiment. From there, Srikanth told if you are sitting exactly on L1 point, because of the sun RF, ground station will not receive signal. So then you have to have a different design to meet the requirement of having a continuous telemetry from that. So in this slide, I tried to summarize the different experiments. Even in MOM also, we need to have a continuous telemetry, but there were certain occasions, every alternate year, you have a blackout and whiteout of the communication. Because either sun will be in the opposite or sun will be in the what you call backside. In both the conditions, you will not get the signal to the ground. So what you have to do according. These are all the challenges which I am trying. Now another challenge in any mission, this is one example which I am trying to show is a long range missions. Mars, which one we have done, whereas NASA's, it has gone beyond the Pluto, Voyager. So what kind of a challenges will be there if you go for initially you make an antenna on board, ground antenna, one particular specification. The moment you travel for a longer ranges, how do you manage the entire mission? This is especially very, very important in terms of the life of a mission. See, we planned this mission as 1 year, it worked for 6 years, right? So if you go for a long range, so from low Earth to geostationary, which is communication mainly, lunar missions and other planetary missions. So in future, suppose if you have a mission which you want to be beyond solar system, what is the need, ground system, how you have to design. So with those requirements, like from the beginning of like 40 years back to till date, ISTRAC, our ground system supporting center of where I work, we have evolved over the years. We are meeting for all the challenges which are posed, whether it is a Gaganyaan related or a Mars mission or even landing mission, even in future, any like beyond solar system or Venus mission, you have to get prepared. So that's the saga which I'm trying to narrate to you is, see, I'm not going more details of the technicalities because it involves mechanical department, electronics department, communication, many experts who have worked on it. I will just give you a glimpse of it. So this is a 32-meter antenna where I will be explaining in this one. So what we do is mainly TTC support, we say, telemetry, telecommand. Then we have so far we have supported low Earth orbiting satellite, lunar and planetary missions. Then we have these, see what is happening in India. Maybe if you look back your Doordarshan days, people used to transmit the time. I don't know how many of you in this hall know, but maybe elders will be knowing. They will set their clock looking at the Doordarshan. That means we were dependent on time on somebody. That is coming from Delhi. There was a National Physical Laboratory where they had one clock. They used to calibrate with the London clock. So we were not independent with respect to time. Today, you can all proudly say that India is independent in terms of time. We have our own time, which is transmitted from my center, Bailalu, where we have major clock. Now we have all ISRO centers are connected with that time. Even if London doesn't give time to us, IUPAC, that center is there, no? Where only you get the transfer. Everybody has to go all over the world. People has to get calibrated. Now nobody goes, but they can have a connectivity. Even GPS, which is giving you like all your mobiles are GPS time synced. Now we are working towards your mobile also should have NAVIC time. Right now we are in the process of it. Now we have generation of time. That's another center which we are working. Some radar development system which I will cover it. Mainly I want the students to look at the science data from Chandrayaan 1 to till date. You will be surprised. Chandrayaan 1 was in 2008. Just before Chandrayaan 3 launch, one paper was published using the Chandrayaan 1 data. So the data is highly valuable, irrespective of whether Chandrayaan 3 or Chandrayaan 1. It's don't worry that I have to work only on latest mission. If some of you are interested in Chandrayaan 1, it is possible to do good science from whatever the mission is there. So that I will try to show you how to access the data. Then there is search and rescue, which we do it, that I will skip it because it is not part of the plan. Space situational awareness, little bit I will try to give you. This is our campus. 40 years back, it was looking like. This is 11-meter antenna. Remember now, when I say the number for any antenna, it's a diameter of the antenna. Most of you can understand antenna because all of you are seeing the DTH, right? If you just do the anatomy of your DTH antenna, you can clearly understand. But that is one way, because from 36,000, you are getting the cricket live commentary. But here, this is not one way. So this is called Bangalore 1, Bangalore 2. Before coming to Bangalore, the ground systems were there in first Tumba. From Tumba, it is moved to Sriharikota. Then after, maybe somewhere around 80s, it is moved to Bangalore. But we have ground stations. When I say ground stations, antennas all across the globe. I will show you those things. This is the place where the landing happened, not the moon. Huh? This is Mission Operation Complex in Pune, where landing sequences are controlled. This is the brain center of ISRO. Even today, more than 26, 27 satellites are being controlled here. This is another building which we call it as a Mission Operation Complex. Inside this visuals, you might have seen it. Mostly Srikanth, you might have seen standing next to the Somnath and presenting. Okay, this is a place where we call MOX 2, and this is the Space Debris Control Center. Yeah, now where all our ground stations are there? Bangalore, Trivandrum, Sriharikota, Lucknow, which are Indian, up to Port Blair. There are outside India stations also. Now, here question comes, why do you need it? Because I told you, depending upon the orbital geometry, whether it's a polar or equatorial or inclined, you need to have. But everywhere do you have? We don't have everywhere. Sometimes we have to hire it. They are like, for example, Hawaii. We use it for Chandrayaan 2 for payload data. And you have here Antarctica. Our own ISRO people will go there. We have a station there where you can, because see, on polar regions, continuous visibility of the spacecraft will be there. So more data dump, more control will be there. So we have our own stations as well as we will hire few stations. Yeah, this is the Bailalu where I work. This is a 32-meter antenna. You have BL5, we say, new antenna, which is newly designed for Aditya, because it is for the first time we are doing telemetry in X-band. So I told you, new requirement was posed by Aditya mission is telemetry should be in X-band. Whereas earlier we were only doing in S-band. I think you understand S-band means 2 gigahertz, 2 to 4 gigahertz. C means 4 to 8, like 8 to 10. That band is there. You can look at it in the frequency band. So this is a 32-meter, 18-meter, two 18-meter antennas are there, two 11-meter antennas are there. This is a huge campus where 105-acre land where this is ISSDC where we work. It's a repository of all planetary and science missions of ISRO, where you can access sitting in IIT only. issdc.gov.in is the website where you can download. I will show you that website also. And this was established in 2003 time scale for the requirement of Chandrayaan-1. One station which is established D18, it's an imported antenna. Rest are all indigenous, developed by ECL and other Indian companies. Yeah, this is how it looks. If you have studied conic section, the best way to visualize any antenna is a conic section. So this is a parabola, this is a hyperbola. Center you have a circle, many elliptical reflectors are here. What is happening? Any radiation which is coming from the deep sky, they are in parallel in nature. When they impact on this particular parabola, at the foci of the antenna, you have to keep one more antenna, which is called secondary reflector, which reflects that till now it is all passive. Once it reaches to inside, this is the beam wave guide. If you are studying RF, you will understand beam wave guide, where once it reaches inside, you will have low noise amplifier. Then you have to convert analog signal into digital signal, then send the data to science data center. This is how the 11-meter antenna looks. And this is shipboard terminal. I will show you a few video and pictures of the shipboard terminal. What was the need for shipboard terminal? Little more details about the design. Generally, when a new requirement comes, this I have explained with respect to 32-meter antenna, mechanical team will go for the design based on the requirements. Then they will analyze it. Then hardware realization will happen. And once hardware is ready, they will come for integration and commissioning. This has been done around 2003 to 2008 time scale. D32 was declared operational. You can see how antenna gets integrated. Those who are mechanical engineer, you have to make each and every part. But when you are integrating it, the parabola, that surface, what you call smoothness, they will do laser interferometry to make the surface uniform, so that any reflected signal should focus at the what you call foci of that parabola, hyperbola, and should go it. That is an important physics application to make surface smooth, whereby people can have all reflected signal reaching to the amplifier. This is some more information about the different types of feed antenna. This is both electronics and mechanical team can work on it. They can design. We have now both S-band, X-band, K-band. Earlier, we were only having S and X. We can have all three together in the same antenna system. This is inside how it looks. Now, whatever you have seen outside, a lot of computer systems are needed now. Once the RF signal reaches down, you have to convert that into digital. You will have a station computer. Antenna, we should be in a position to offer our services to the any space agency also. We call it as a CCSDS, Consultative Committee on Data Standards. As per that, we have to qualify the station. Different location, Brunei ground station, Lucknow ground station. Any one ground station, general principle is RF ingestion, RF converting into digital, from digital to converting that into a useful data, whether it is a telemetry or the payload data. The reverse is also same way. Any like Srikanth wants to switch on the camera means he will make analysis and send that signal in one particular command. That command gets converted into analog signal. Since it has to, suppose if it is a Mars mission, longer range, if it is a moon, 4 lakh kilometers, depending upon that, the power of antenna will be variation, 2 kilowatt to up to 20 kilowatt our ground stations are capable. Now, if you look at any the launch trajectory, one is this near equatorial, another is south pole. So this will dictate you where all I need to have. We have a standard ground station. Under certain circumstances only, we may go for a ship-based because you don't have a ground station or land mass is not there. On that particular situation, you have to make smaller antenna, either 4.5 or 7 meter antenna, which will be positioned on a ship. You have to work with the Navy, take the ship and position it. For Mars mission, even for Chandrayaan 3 was there. For Aditya, 2 shipboard terminals were there. So it will be positioned depending upon the trajectory. This is a south pole moving southern trajectory. This is equatorial eastern trajectory. A small glimpse, it is not my domain, but it is better to understand spacecraft operations. Once the ground station is ready, satellite is in space, data starts coming to it. So you have to, whatever the inputs to the mission, it will go there. Then you have to establish a ground segment. Then there is a checkout in URSC, they will do that. Ground systems will be participating in any space mission. So then once it is commissioned, in the normal phase, like Srikanth is now handed over the Chandrayaan 2 or Aditya, as a normal phase, our ISRO will take care of those things. Then till the decommissioning phase. One best example for decommissioning phase is megatropics. You can have a look at it. How an active, good satellite, we have set the benchmark, how it can be decommissioned. It's a very interesting experiment conducted by in the megatropics. We have re-entered that one. Yeah, there are around 26, I think now maybe 27, no sir. 27 satellites are there, which are being monitored and controlled by our ground systems. Different, this I will skip it. Navigation, yeah, I told you about the navigation that we have now indigenous time. Similarly, navigation also is going to come up, similar to GPS. There are a few satellites are going to be launched. For that, different, what is happening there, the ground system requirement is different. One thing is you have to maintain satellite which is in exact position there. How do you maintain? You have to range every day. Whereas in case of Chandrayaan or Mars mission, when it is traveling, I want to know its position. We call it as ranging means position, but it is dynamically changing. Whereas in case of these NAVIC satellites, satellites are at a fixed position. There will be little drift in the position, which I have to correct always. If I know the satellite position with respect to a known ground station, like 3 ground station, then I can tell one moving object where exactly your position is. That's the principle of GPS. So for that purposes, we have established various ground stations, smaller ground stations, which we call it a ranging stations, we call it. That will be operating and they will be talking to satellite and the ranging position will be known. Then they will update that position as well as the time which is generated using the maser clock will be uploaded to satellite. From that satellite, position and time will be transmitted to unknown position mover, like unknown any navigation agency. This is how the satellite constellation which is there. We call it as a navigation Indian constellation. One new satellite is being added to it. Few more satellites are expected. It will be operational very soon. This is a timing scale system. We have up to picosecond time scale. This is very, very important when you are going for a long range like Mars mission, Pluto mission. Time is very, very essential. You should have an order of nano is not sufficient, picosecond only. Then only your range measurements will be very accurate. For that purposes now, we are self-reliant with respect to the time. This another important, those who are computer science students. With all these things, you should have a very good, highly secure, very reliable computer network. All operations are, see, you may be any engineer, mechanical or electronics, computer knowledge is essential. So for the success of any space mission, computer network also plays an important role. So we have a very good computer network, both in the ground control center, where we give like any mission, like 20 years back mission data, if you want to analyze, they will be for some study purposes, they want to study SRE data, they want to study that is available. That is very, very essential for the current success of the mission and future planning. We store the data, archive the data of all spacecrafts. And this is very, very essential. Like Bharat sir was telling, NGC software, more than 1 lakh lines for that. Mostly 90% all softwares inside ISRO are indigenous, in-house developed. There are certain COTS software, commercially off-the-shelf softwares. These are some of the example real-time data which is used for vehicle. This is for payload data. They are all written by our own engineers, monitoring and control software, schedulers. Then this is an international protocol for all ground stations. We have to follow certain international protocol. So software plays an important role in a ground system for the success of the mission. If you recall the landing sequence, no, I don't know, Srikanth will permit me. It will take 3 to 4 days to completely review it. And they will uplink. It is not that on the landing day, half an hour before, it is not uplinked. So much exercise is being done, 3 to 4 days. They have to verify using softwares. Every command has to be verified using software. He may be expert. He will say that this command perfect. Yeah. There will be peer reviewers. They will review using the softwares that command is there or not. Then they will uplinking. So that's how software plays very, very important. Like he was telling, all of you are interested in AI, ML, all those things. Go to a private industry, earn money. I appeal those who are interested in AI, ML, please learn it. Come to the space industry, aerospace industry. You may get more money in the private sector, but it is very, very, he said, you work for the nation. Software engineers, we draw your attention. Please come to ISRO space industry where you can contribute a lot. Little more other technology you need to learn, you will learn through in the process. This is how the one glimpse of the software, different softwares, how it looks. People will be monitoring regularly. Whatever you have seen during the launch time, whether it is a mission control center at Sriharikota or our ISTRAC, similar pages will be there depending upon the feedback to mission director. How does mission director operate? Mission director will sit like this only, a center he will be sitting there. All subsystem engineer will monitor, they will have a communication with them. They will say that the solar power system people, please clear. Then they will say the antenna subsystem, communication system, please clear it, like that. So for that, entire network should be efficiently working. And this display system should be very, what you call, comfortable and easy to understand. I have clumsed it here, but each one is one particular thing. Yeah. Now, so once the launch vehicle or a satellite, you need an antenna, you need an RF signal to connect, right? But once the ground station receives the data, suppose you have a ground station in Port Blair or you have ground station in the other port like JPL or American, how do you get this data? Even though it is less important, people say, but it is very crucial. The data should be transmitted immediately without much delay to the ground control center where they will make a decision. For that, you need a wide, doubly redundant, highly reliable communication network. Like you have a Geo, Reliance, then BSNL. Like that, we have also satellite-based communication links for depending upon the criticality of the event. Suppose you are doing lunar orbit insertion, right? That's a critical event is being done. During that process, I don't want to lose the data. This is a requirement given by the mission. I will say, sir, one antenna. He will. No, I will not accept one antenna. I need communication link should be multi, at least 2 to 3. Double redundance or triple. For Gaganyaan, no, they're saying triple redundant. In one of the talks, Russian astronaut said they will go for 7 and 8 redundancy when it comes to the human mission. They don't bother about 3 systems failed. They will be peacefully sitting and learning, seeing it. They will have 7, 8 data flowing to that place. Any system failed, they don't bother. We have at least double and triple redundancy in case of Gaganyaan. So communication link place, it's a hybrid link now. I can use terrestrial link. I can combine that to a satellite link. For satellite support, there are certain fiber links will be there for launch vehicle support. Even sometimes other space agencies also will give you the communication link support. For societal application also, you need the communication link. Various SpaceNet services, Like many of our the ISRO centers are connected using this type of communication link. Recently, it's not very recent, but 10 years back, this service started. I think IIT also may be having NKN, right? If not, please work on it to get that one. It's a national knowledge network. It's a free internet services. We use this one for sending the data. Like yesterday in Aditya, one payload was operated, magnetometer. When that data comes to us, we have to process and give it to a person who is sitting in VSSC. So we use under circumstances NKN. So data sharing things. Similarly, navigation related network is there. Then you have the Inmarsat where you can get the data from different satellites. So communication link plays very important role for the success of the mission. Suppose launch is done, like INSAT 3D or one example is there. Launch is done, no antenna is tracking. No antenna was able to track it because they didn't know where exactly the position was there. There's one more important service in the ground system is called as the moment satellite is injected, somebody has to tell where exactly satellite is there. It is called as a preliminary orbit determination. I didn't bring the slide, but that is important mathematical application. They will calculate the exact position of the spacecraft. From there, they will calculate the trajectory, whether it's elliptic, what is the perigee and apogee. If you have seen any launch, they will immediately declare, they will say, no, satellite separated, they will say. Below one, you will see perigee and apogee will be declared. That is done by one of our department called POD, preliminary orbit. It's a pure mathematicians. All mathematicians are working in that. No engineer will be working there. These are certain facilities. I may be very close to concluding my session. These are the different radar systems. Of course, why radars are important in launch vehicle means, how do you decide your launch time? Suppose in conditions. So that's the reason that every half an hour, they do weather forecasting. 1 week before onwards, they start weather forecasting. That is there in Sriharikota. These are the antennas, radar antennas, which will support the launch vehicles. Yeah, this is our ISSDC where I work, where we are hosting all the data there. Chandrayana 1, 2, 3, Mars mission. These are future missions which we will be hosting. All these data which are available, please log into issdc.gov.in. You can projects can be done sitting in IIT itself. Even if you are AML fellow, you need 1 terabyte test database. Who will give you in IIT? You want 10 terabyte test base. Who will give you? We can give you. You just log into us. AstroSat, I have 16 to 20 terabyte data. I have Chandrayaan, very good data. You can do both science experiment, science research, as well as the data science research also. We host more than 1 petabyte data in our ISDC. You can download, you can do your own projects. This is a future challenge which we are also working towards it. What is new element in this other than the regular ground segment? We are going for a relay satellite based. Suppose when you are going, like man is there in orbit for 7 days or 7 orbit. When he is in orbit, the current ground stations has gaps. How do you fill the gaps? I cannot install the ground station in ocean, or I can keep for a long time my shipboard terminal in ocean. So what they are thinking is 3 different satellites in 120-degree apart, which NASA is already doing for last 40 years. Even China has it. It's called as the relay satellites. That's a new, it's not very new, but for us, we are also working towards that. Once the satellite comes up, then you need to have a 24/7 connectivity with the crew. Otherwise, it will be difficult. We have to monitor his health. That's a new challenge, new direction. The Gaganyaan. This is how the schematic diagram of see, this is what I was mentioning. We call it as IDRSS, Relay Satellite System. I means Indian Data Relay Satellite System, where you will have multiple ground stations will be talking to this, whereas these 3 satellites, minimum 3 is required, can monitor the crew in the space. Yeah, this is Gaganyaan related, some more pictures I have put. I think this is a ship-based terminal, how it operates. It is like a ready-made. I think what I understand in Chandrayaan 3 is within 7 days, we have made ready 1 shipboard terminal on the ocean. If it is on a ground, within 1 day, we can make the station ready. Suppose you have, let's say I want to track from Tirupati, there is no antenna. From only Bangalore to Tirupati, I have to move my shipboard terminal. It's now terminal, it's not shipboard. Within a day, we can make it ready and you can start tracking from here. I mean, these are all the new way of collaboration. You can think of it like here a day. Can we track? These are all the new ideas where collaboration is possible. It's only a technological understanding only. How to track a satellite, you will not be able to. Either you have to come to ISRO, sit with them, and since shipboard terminals are available when it is not being used for any missions, you can propose, ask for it. It can come over here. They can also demonstrate. It is possible. Our director is very much open in encouraging academia collaboration, where 1 week it can be here and it can track one satellite, which we do it there for student projects. They come there, establishing a communication link with satellite is a project. They do it like that. Yeah, this is future project. What is happening is there are certain requirements are there. One is you are having 32-meter antenna, whereas if you go to America, they have 64, 55, huge number of antennas. They say that it is a very costly affair, white elephant. Maintaining that antenna is very difficult. Can you achieve whatever service is given by the larger antennas with a smaller antenna using aperture synthesis methods? That is the new thing which people are working on it. Even ISRO is working in that direction. Then with the single antenna, can you track multiple satellites? When 2 satellites are there, I can see 2 satellites, which call is visibility. But how do you track multiple? That is also another area which people are working on it. This is a space situational awareness. This is an important thing which ISRO is also gearing up, and we are in a better position now. Lot of telescopes and radar antennas are being established across India. This is mainly to know the debris which are in the orbit. If you have seen the launch of Chandrayaan-3, it was postponed by, I think, 4 seconds or 1 second, sir. 4 seconds. 4 seconds it was postponed. It was decided in our, there is one department, that's called SOPA, this is Proximity Analysis Division. They will make a conclusion, and in Sriharikota, they will take that decision. So debris monitoring is very, very essential. Like I told you, megatropics re-entry also, those decisions will be taken by this particular department, where they need a lot of data. At present, we are not in a position to generate the data on the debris, whereas we know our satellite positions, what are all there. Whereas the NORAD agency is there, which they freely give access to that data. We are in the process of building our own observatories to observe up to, I think, 10 centimeter size of objects also. You have to observe, track it, catalog it. If you happen to log into what you call as a Skyview website, they will tell you every 10 o'clock, as on today, 27,585 objects are known, are available. Like that is available in public domain now. Every day, this department in our ISTRAC, they will be looking at, because any collision may happen. One of the important experiments was done in Chandrayaan-2 and LRO. Both were about to collide. LRO cautioned us. Then they together worked. Either you raise your orbit or reduce, whatever may be the convenient, you have to do collision avoidance. Yeah, the same thing. I think I have one URL. You can access the data. That is very important. Please, I request, like those who want to work in future for Aditya or Chandrayaan-1, Chandrayaan-2, you please type ISSDC. You will go here. Hope it will work fast. This is our website where you can download all the astrosats. Even for astrosat, those who are interested in astronomy, they can propose. Right now, we are starting the 13th proposal cycle from October onwards. Like you can understand the 9 years over. Chandrayaan-1, just click here. You can go to the data. New portal will come up. Just go here. Just log in here. Search for your interested data. You can do a blind search if you don't know anything. Data comes up. I'm very happy it is running fast here. In many times I used to struggle. Internet is very good. This is one imaging data I'm just trying to show you. Those who are interested in understanding the image, they can download image. Those who are interested in the other data like moon mineralogy mapper data they can download. Then radar data, recently we published it. You can download DEMs. Even here, blind search, if I do it, yeah, it's very fast, sir. You're very good. Even in my ISSDC, I will be slow. Where server is sitting there. So you can download a lot of information you can study. It's very simple. Please, I request all students, any type of, need not be science publication alone. You can do some computational projects also, small short-term project, 3 months or 6 months, whatever it is. This is only Chandrayaan-1 I have shown. Similarly, if you go to AstroSat, you can just go here and start your own proposal. If you want to observe M51, Andromeda, or any black hole, you can just go here. I think this fellow is a little slow, maybe. Okay, there is a proposer guide is there. You can just see the rules. This is the Astro Browse is a place where you can download the already proposed proposals data. If I can show it. Registration is required, whereas America and other agencies, they are doing free of cost. I mean, free in the sense, no credentials required, directly you can, but still we are having, maybe in future. Okay, I think you can try it out. I will not just go into that one. It's working fine. Every day people are accessing our website, downloading the data. Just to propose, you need certain background. Please go through these things. Astroviewer means what? As a scheduler, all those things, you please go through it. How to propose for, I mean, it may be difficult for at the graduate level, but we can help you. There is a space science program office in our ISRO headquarters. They will train how to put a proposal. There is a IUCA AstroSat support cell. They will also give periodically every 3 months, 6 months, one training will be given to the interested astronomers and researchers. You can have a look at it. This is one thing. Last, hope my time is up, right? This one interesting thing which I wanted to show. This is related to the ground systems. Yeah. At present, which station is doing tracking of which satellite? Suppose if you look at, now since the next you are going to listen Aditya, let's look at the 65th, like this is station antenna name. 65, it is tracking SOHO, solar orbiting helio spacecraft. Look at the antenna. You can see what is the range, 1.5 million kilometer. Our Aditya L1 also will go same 15 lakh kilometer. I think only this antenna is not working now. Maybe they have not deployed for any spacecraft. Whereas like this facility is there within ISRO, not similar to this. Within ISRO, we know scheduling which antenna is being used for which. This is a beautiful application. Like maybe those who are good at software, they can collaborate with ISRO and give a, like IIT Kanpur, I think Kanpur has given scheduling software way back, very long back, 25, 30 years back. Even today, there is a collaboration with the IIT Kanpur that how to schedule the ground stations. How many satellites are there? When AOS, LOS will happen? How to schedule one particular ground station? This is one such application. It is in public domain. We are not in this level. Maybe whoever comes forward as a collaborative project, how to make this small example I'm saying, need not be the same thing. You just go to this KPLO. This is Korean lunar orbiter. There are more than 8 or 9, approximately 10 orbiters are there around moon. You can look at it. This is MAVEN, Mars Orbiter missions. Maybe 2 years back, if you have looked at it, they would have written MOM also here. MOM was being tracked. One thing, it's off the record is, Chandrayaan-3 is fully independent. Aditya is even more independent. We are not depending on external agencies. Of course, there are certain things. I'm saying not exactly 100%. We are moving in that direction to have, even we are thinking to have our own ground station, which are possible like deep space antennas. Because what is happening now, JPL, NASA, they are also busy with, there are many missions. Whenever you want, they may not give you, even if you pay money or technical cooperation, whatever may be the mode, because they are also busy. Our missions also now, there is a increased focus to have more scientific missions or scientific projects. Means we should also be get prepared to have our own systems, but fairly we are in that direction. Hopefully in future we will have more in that direction. I think with this I may stop. So many things are there. Thank you so much for giving opportunity. Especially I want to say thanks to Arvinda. He says I have inspired him. I say he has inspired me. He is a very good researcher. Thanks to Ratish and my other fellow colleagues Shrikant and Shankar and Bharat, because they have accompanied on my request. We had a difficulty or easy, whatever may be, because we wanted to come here and make this event successful. One small suggestion, as we are aware that 23rd August is declared as the National Space Day. Assume that we are celebrating today. This itself as a National Space Day. Please continue this every year, shifting the date from 4th November to 23rd August if possible. Next year also, many of us, we will help you. Other fellow colleagues who are equally good like us in ISRO or even other aerospace industry, you please bring them here. If possible, try to keep this as a every year event in future. It may be benefiting many students. Thank you.
Thanks, sir. Thanks for wonderful talk and all the details of this thing. And now I request Dr. Ritesh, HOD Physics, to give the memento to Srinath sir. Thank you all. And now we have a lunch break. There are these rooms we have arranged. Who that side, there will be volunteers, you can say. Whoever brought the lunch as we have instructed, you can have there. And we will start our next session by 2 o'clock. 2:30, sorry. So next session by 2:30, there's a talk. And after that, we have an interaction session, which is an important. So there, you sorry we could not give a time to ask the questions here because of the time constraint, and we have a dedicated session after the tea break. So there you can ask whatever you want, and then you can explore the questions and other things. Okay, so please join by 2 exactly by 2:30. And who are the students here, just be careful while traveling within the campus. Okay, thank you.
Hello, Adibala.
No problem, no problem.
Hello. Hello. Adibala. Am I audible? No.
Minus one. Minus one.
Hello. I'm using it. Yeah. Am I audible? Okay. So
Welcome all. Please be seated, all the students. And our afternoon session is about to start. In the morning session, we have learned all the scientific details about the launch and the mission, satellites and all. And now we will explore why do we do all these things from the scientific discoveries, what and all we are going to achieve from that. And we have our eminent speaker, Dr. Shankara Subramanian. Let me introduce Dr. Shankar Subramaniam. He is currently principal scientist of Aditya L1 mission and also principal investigator of solar low energy X-ray spectrometer on board Aditya L1. He is heading the space astronomy group of URSC, UR Rao Satellite Center, ISRO. He completed his master's in physics from American College, Madurai. He carried out his PhD in physics from Indian Institute of Astrophysics, Bengaluru. His research areas of interest is solar magnetic field, optics, and solar instrumentation. He carried out his postdoctoral research at the National Solar Observatory, USA from 2000 to 2006. He joined URSC in March 2006 and currently heading the Space Astronomy Group. He has more than 10 years of expertise in optical, NIR, UV, and X-ray instrumentations for ground as well as space-based observatories. At different capacity, he has contributed to AstroSat, Chandrayaan-1, Chandrayaan-2, Chandrayaan-3 science payloads. He has more than 100 papers in national as well as international journals and also a member of International Astronomical Union, Astronomical Society of India, and Optical Society of India. Sir, please welcome.
Thank you, Arvind. Okay, being a session after lunch, I have to be a bit more careful. So I just make it more interactive. So how many of you are interested in looking at the sky? Everyone, right? That's a curiosity. Okay. How many of you want to know more about what is in the sky? That is a knowledge. So the curiosity will drive you to know the knowledge. And these two are important for you to advance in any aspects of it. So I just want to bring to your attention that science and technology has to go together. Because if you want to do great science, you also need to have a great technology. Without technology, achieving a science is very important. I mean, it's very difficult. And of course, when you want to advance the science, you also start inventing on the technologies. Okay. So how many of you have mobile phone in your hand? All of you, right? Mobile phone has a camera. Okay. The camera has a small, very small chip, right? Any one of you know how this chip was, discovered or invented or developed? Actually, that is what developed for an astronomical purposes. Then it got into a spin-off into an actual everyday life. Because the sources what we are looking at is very, very far away. So for you to image the sources, you need to have a very, very good imaging systems. That is how the detectors, like what you have in the camera was invented, and that is now is in everybody's hand now. So science and technology goes together, and that is how we the technology help us to improve on the science, and the science help us to improve on the technology. Okay, today I'm going to talk about our own star, the sun. So it's like you living with your friend, correct? Many times you find that if your friend is not there with you, you will feel the life is bored, right? How many of you think that if the sun is not there, what would happen to the earth? Suppose tomorrow the sun says, no, I got bored with you guys, I'm going to go somewhere. What do you feel? What would happen? Earth will become frozen because sun gives you the temperature, the warmer environment is given by the sun. What else? Earth will not revolve. That's a good answer. So the earth revolves around the sun. If sun is not there, all your Kepler's law is gone off. What else?
living organisms cannot grow. So all this, your food chain gets broken, so you can't live. So sun is an important element for our everyday life, right? So understanding of the sun and making it not to get bored with us is an important element for any of the scientists. So our aim here is to try to teach you what we know about the sun, why it is important to study the sun, and how Aditya is going to help us in moving forward to that. Okay, so I think this crowd is good enough to understand this. What I'm showing here is Milky Way galaxies. Yeah, very good. I mean, at your age, I would not have been able to answer this. Okay, so so this is an artistic impression of the Milky Way galaxies, and you see the size of this. We usually call them in kiloparsec because the numbers are huge. The size of this is about 27 kiloparsecs, and 1 parsec is somewhere around this much of distance. Just for you to understand, if you travel between south and north of India, you have to travel 500 crore times for you to cross the Milky Way from one end to the other end. That is the size of your galaxies where we are living in, okay? And then we also have, within the galaxies, we also have a system called solar system. And what you see here is, we call it as a heliosphere, which encompasses the sun and all the planets around the sun. Okay, that is called as a solar system, and that is called as a heliosphere. And we do see such a heliospheric pictures from other galaxies and other stars. And we call that as an astrosphere. So heliosphere is not the first one detected by us. The astrospheres were detected, and then we know that heliosphere is existing in our own galaxies. Okay, I think most of you had answered it. Why do we study? Essential for life on Earth. And of course, understand the physics being from the science background. We also want to know how the sun is formed, how it is going to evolve, and how long the sun is going to live, because that is related to our own life. And it's also called unmanned laboratory because some of the conditions which is existing in stars, especially the sun, you can't create it in the laboratory. So, so if I want to understand a small phenomenon in the physics, usually what we do is we create the conditions in the laboratory, try to mimic what is happening in that particular physics, and try to understand it. But being in this surrounding where you have a temperature, pressure, everything is, defined, some of the physics you won't be able to do it on the ground. A simple example is the fusion reactions. How many of you know about fusion? Many of you. What does the fusion does? It just takes 2 protons, fuse them, and generate the energy, right? That's what is happening in the sun all the time. Hundreds and thousands of protons gets fused every second in the sun. But for us to fuse the 2 protons and create the required energy for our electricity, we are still not successful to do that. So what we learn from how the fusion reaction happens on the sun helps us to generate a laboratory conditions where we can fuse the reactions, fuse the protons. Similarly, there are a lot of physics which happens on the sun, cannot be done on the ground. So we do look at sun as a laboratory where we understand the physics from it much better than do it on the laboratory. Of course, sun being closer to us, we use it to understand the other stars. Other stars, when I say stars which are similar to the sun, we have a gamut of stars which has totally different properties than the sun, but sun-like stars is something which we can understand by looking at the sun. And since the sun is nearby, I can see the sun as a big ball of fire. Whereas the stars, we can only say twinkle, twinkle, little star, right? We can't even resolve them. So this is some aspects which helps us to understand a greater effect. And of course, it has a vast effect on our own planet Earth, both a good properties which you guys have told, and there are also a kind of a property which is a hindrance to many of us going into the space. I will just touch upon those elements to it in a bit. And of course, if any of you are physics students, many people come and ask me, can I do astrophysics as a specialization? My advice would be study the physics, because astrophysics is nothing but the applied physics. So if I look at sun and look at whatever physics I can think about it, what I have studied in my bachelor's and master's, I can apply all the physics on the sun. Similarly for other stars. So what you learn now in your BSc, MSc, or engineering physics is an applications to your future if you take up your career in astronomy or any other space physics related aspects. So we do study plasma physics, we do see atomic and molecular physics from the sun. And many of this is applied to our solar system planets as well as the extrasolar planets. I mean, there's a lot of interest to look at planets which is away from our own solar system and try to understand whether those extraplanetary systems are very similar to our own solar system. Okay, so now the sun is not quiet. I mean, if it is quiet, I think it'll be very boring. I mean, it's like your young kid. Young kid, if they are quiet, they are not very interesting. Kid has to, I mean, go, fight, everything you have to do. So what you see here is a lot of activities which is going on the sun. Please note that this kind of detail is available only from sun. No other stars you can study to this detail. You see that there's a lot of, I mean, you see the bright regions which is going up and throwing matter into the space. We call that as a flares, solar flares. It's nothing but huge amount of energy which is released into the space. We call that as a solar flares. And this is a flare which happened sometime in 2003 Halloween time, similar time, November 1st or so. Effect on, I mean, though I think we are not affected for the good reason that we are protected by our Earth's magnetic field. So many of these events which is happening on the sun doesn't reach to the ground level where we are here, correct? Whereas the system on space, I mean, if you look at the image, you see at the end of the image, you see this black and white structure. Okay, in all the images captured by this spacecraft, this mission, you will see at the end of it, you will see there is a lot of black and white grainy structures. What you get is nothing but the material which is thrown from the sun, coming and hitting your spacecraft, hitting the imaging system, because the imaging systems, what you have, I mean, what you have it in your hand, mobile also, is a silicon wafers. The silicon is sensitive to these high energy particles. The particles deposit a lot of energy into the imaging systems. So what you see here is a salt and pepper structure. Is nothing but the particles coming and depositing the energy on the system. Of course, if the energy is reasonable, the system survives. If it is very high energy, the system can collapse. So that is the danger of having a space systems in space outside of Earth's magnetosphere. The plasma or the particles ejected by the sun can destroy your system or can make it non-functional. Of course, we do a lot of basic background studies before we have a system built for taking care of this. There is a separate study which we go through it, but this is an important element when we launch a satellite. We want to make sure that it doesn't get disturbed by these systems. This is a picture I need to explain it here. It's taken by a NASA mission called Stereo. What is in the center is the sun. I'll try to run it again. So what is in the center is the sun, and what you have here is the earth. So we are in space looking at the sun-earth line, and you can see that the particle whichever is ejected can reach up to the earth. Okay, it goes up to the earth, and of course beyond to that also. It doesn't come into the earth because you are protected by the magnetic field. Of course, the magnetic field has a what you call a way particles to come to the earth's through the polar regions. All this aurora borealis, what you see, is nothing but the particles which is coming and depositing their energy on the earth's atmosphere in the north and south poles. And that is how you get these auroras, beautiful auroras. What you see is from these particles which are coming into the earth's atmosphere. This is a image made from our own system called, in Ooty radio telescope. What you see again here is the sun sitting here, and you have this earth, and you can see that the huge amount of matter which is thrown into the space is traveling and reaching to the earth, and of course other solar planetary systems too. Okay, so coming back to the heliosphere, what we talked about. So you have this solar system, and this is the region where our heliosphere ends. You can say we call that as a heliopause. And pretty recently, maybe within less than the last decade, this mission Voyager 1, which was launched somewhere before, just after I was born, this has crossed the heliopause. We know what is the distance of the heliopause now from this beautiful mission. And okay, this inner heliopause. And we also know that the mass which is thrown into the interplanetary medium doesn't stop with our own solar system. This Voyager, which went out of the heliopause, started to see these the mass ejections. We call it as a coronal mass ejections from the sun, even crossing the heliopause. Until then, we were thinking that the outside of the heliosphere is a pristine region where you don't have any information from the solar system. But we know that the mass from the sun does cross the heliopause and goes out into the interstellar space. We call that as an interstellar space, the space between the two solar systems. Now, so far what I talked about is the dynamic system, which may happen once in a while. It's not that every day it's going to happen. Of course, during solar maximum, which we are almost in the solar maximum, where more activities happen, you may see every day there may be a flare or CMEs currently. But during solar minimum, maybe after say 6 years or so, you may not have an everyday activity, but you will still start to see the plasma flowing in the interplanetary medium continuously. This we call it as a solar wind. It's like what you have the wind in the normal conditions. In the interplanetary space, you have particles which is keep on coming from the sun continuously. Okay, so the typical mass is, the solar wind mass, again, it's a huge number, something like 10 power 36 grams per second is thrown into the interplanetary medium. It's a huge amount of mass which is coming continuously from the sun. These particles can also affect some of your systems if your system is not very, if your system is very sensitive to these particles. And of course, we do measure different properties of the solar wind, as well as the mass ejections coming from the sun, for us to understand what kind of particles it has, what kind of velocities it is coming with, which will help us to know when this particle is going to reach at different, different positions in the sun-earth distances. Now coming to Aditya L1, so what have so far talked about is you have a sun, you have a solar flares, you have a coronal mass ejections, and you also have a solar wind which is continuously coming from the sun. You also see that there is a magnetic field lines which is coming from the sun, because sun is a ball of gas which also has a magnetic field lines. And since sun rotates, the magnetic field lines are not straight. That is a curly ones. So what you see here is a curly structure, the gray lines, or the magnetic field lines coming from the sun all the way in the interplanetary medium. So you have flares, coronal mass ejections, and then the solar wind where the particles get along with the magnetic field lines, because the charged particles cannot cross the magnetic field lines, so they have to travel along the magnetic field lines. From your Maxwell's equations, which you study in your BScs or in the physics. So these energetic particles will travel along the magnetic field lines, and at some point of the time will reach the Earth. So that is the basic principle of how the sun can affect the Earth. So Aditya will be, we are not just going to the sun, we are just near to the Earth compared to the distance from the sun and Earth. But we will be sampling these informations well ahead before it reaches the Earth. So typically about a few hours to a few days before the particles can reach the Earth, Aditya L1 will start to see these events at the L1 point. Okay, this I'll skip. We carry 7 payloads overall. 4 of them are remote sensing. When I say remote sensing, it's like the sun, the source is somewhere. By looking at the information from the source, I try to understand what is the source is going. That is called the remote sensing. In situ means in situ what is happening in there. Say, for example, people who are watching on the YouTube, they are seeing this as a remote sensing, whereas people who are listening here, you are all in situ. Okay, so that's the difference. So we have 4 remote sensing payload, which looks at the both imaging and spectroscopic of the solar atmosphere. Corona is one aspect of the atmosphere. And of course, photosphere and chromosphere are another layers on the sun in the atmosphere. And we also have X-ray instrumentations, which samples the solar flares. So while coronagraph looks at the coronal mass ejections, X-ray instruments will look at the flares. So you study the flares, you study the CMEs, and you have this in situ payload, which looks at the particles as well as the magnetic field. So by having all these 7 payloads, we study the flares, we study the coronal mass ejections, we also study the energetic particles, which is coming from the sun. We also study the local magnetic fields, which is at the L1 point. So we have a gamut of information which will tell us from the source to the L1 point, how the dynamics is going on. Okay. Okay, I'll just skip this because it's not very important to us. This is for the technologies. I mean, since I told science and technology goes together, I should also tell you what are the major technologies which went into Aditya, which allows us to do certain studies which we could not do it before. Okay, one of the major technologies which is developed by ISRO is the highly polished mirrors. Okay, so just to put the technology in the context, one of the instrument on Aditya has to look at the corona of that. Okay, so many of you would have seen eclipse, solar eclipse, correct? So solar eclipse is needed for you to see the outer layers of the sun, the corona, what we call it as a corona. In the normal circumstances, you can't see the corona because the corona is very, very faint compared to the bright sun. It's like walking on the road in the night where you have a bright lorry coming in front of you. It'll blind you. You won't be able to see the nearby regions. So you have to block the light to see what is surrounding you. So what eclipse does is it blocks the moon, so that the moon blocks the disk of the sun, so that the sun disk light doesn't reaches you, and then you start to see this very beautiful coronal structures, what you see to the sun. So one of the instrument on board Aditya is going to do the eclipse all the time. The eclipse, what you get on ground, is only for few minutes and spread over maybe many years. I mean, you may not get an eclipse every year. Whereas Aditya will give you an eclipse, artificial eclipse, all the time. So this provides us information about the corona continuously all the time. Why we can't do it before? The same question is the contrast what you need. That is, you have a bright object, you have to block the bright object to get the faint structures. And with the nominal technology what we use in the ground-based telescopes, if we use it, it provides the disk light which falls on the mirror will introduce a lot of scatter in the system. I mean, it's very similar to when you drive the night, when you drive in the night with your specs, if your specs is not clear, you will have a lot of scattered light which will go in. You may not be able to see the road properly. Similar conditions, if with a normal mirror, if I image the eclipse, artificial eclipse, I won't be able to see the corona because of the scattered component from it. That's where this highly polished mirrors are important for us to minimize the scatter as much as possible, so that you will start to see the corona even in the normal conditions. So that is a technology which is developed by ISRO laboratory, and it has a lot of applications in high contrast imaging in the future. Okay. Then there are a lot of scientific detectors which has been used on this mission, demands very low noise performance. Okay, when I say very low noise performance, it's like is again like this. When a speaker is speaking, if the audience is talking quite a bit, the voice doesn't reaches to the audience very clearly. Correct? The surrounding has to be quiet for a signal to reach you. Okay, when I am talking to the audience, if the audience also speaks, the information doesn't reach properly. So we need to have a system whose noise is smaller compared to whatever the signal comes in. Typical signal, what I have put it is in here. Say for example, this is a femtocoulomb. I hope many of you know about what is coulomb is. What is the charge of an electron? 1.6 into 10 power minus 19 coulomb, correct? So it's a femtocoulomb means 10 power minus 15 coulomb. So it is like you are looking at something like 10,000 electrons is a kind of noise which you need to have. How does it work is like this. Say I have a photon. I mean photon, when I say light which is coming and interacting on the detector. A photon of certain energy will form certain number of electrons. For example, if I have a 1 kilo electron volt photon, 1 keV photon, which is falling on a silicon detector, which is what there in your camera, will provide about something like 300 electrons. Okay. So if I multiply 300 into 1.6 times 10 power minus 19, that is the kind of charges you develop on your system. That charge needs to be converted into a measurable form. It could be a current or it could be a voltage, so that you know that 1 keV of photon has struck your detector. So that is the kind of noise which you need to have in your system for you to measure such a very low signal informations in it. So these are some of the payloads which are on board Aditya L1, and the typical noise requirements of the system, which was accomplished by doing some kind of an R&D before we brought it to a level where we can fly it in space and get the required data for us to analyze it. Okay, this information is basically tell you that an eclipse sky will have a scatter component which is of the order of less than 10 power minus 9, whereas in the daytime, you have a component which is of the order of 10 power minus 6 and above with a good sky conditions. So with Aditya, will be better than this daytime. Of course, we cannot beat the natural eclipse because natural eclipse is not always a natural event. To do that, we need to have a kind of a formation flying at a distance of Earth and Moon. Earth is a main satellite, Moon is a formation satellite. That satellite can block the sun, and you get an artificial eclipse with a condition which can go to of the order of 10 power minus 9. So that is something which is for our future missions, which we have to keep working on it to get to that level. Another important element which we want to put it in this particular mission is some of the onboard intelligence. And this is where again the technology comes in, because many times, especially solar missions, demands huge data volume, because this is a sun which you can resolve them, and you can also dynamically acquire very fast. So it requires a lot of data volume. So we have provisions for an onboard intelligence to detect these events. Like whenever there is a flare happens, whenever there is a CME happens, we go into a mode where we can take high cadence data. Otherwise, we do a low cadence data. So that is how the data volume and data things are managed. And we also now in the process of doing a on-ground process to indicate that there is an event which has happened on the sun at so and so time. So the telemetry data which we are getting in will be processed, near real time, and provide this information to the ground-based systems and ground-based observatories, enable them to look at this particular event as early as possible, than waiting for the data to come down. Okay, this again, I talked about it. The uniqueness is to go closer to the sun, which means you have to keep the scattering very low. And the magnetic field informations, which is important to study these dynamical events. And one important element which I didn't talk about is the UV band, which Aditya L1 is going to look at it. Is an important band for Sun-Earth connections. Many of you would have talked about this ozone layer depletions, would have studied. The ozone layers has a very good, very important absorption bands in this 200 to 400 nanometer. And the solar radiations in this particular band can affect those ozone layers. So linking the Sun-Earth connections will be done by one of these UV observations, which is not currently available from any missions internationally. So this would provide you great informations. Okay, and where do the institutes or the academic institutes can contribute to Aditya L1, where we have a lot of modeling experts available. Modeling is an important element because the Sun-Earth connections, what we talked about, requires a large-scale modeling to know if I am given an input of this kind of radiations coming from the sun, how is it going to interact in the Earth's environment, how it is going to couple to the Earth's atmosphere, is something which we can do it. And we have been doing this with ISRO Kolkata. And here is an example of a modeling developed by them, how the radiations which is coming and hitting the Earth and its magnetosphere, how it couples to the region closer to the moon. So what you see here is the moon, and what you see here is the Earth. And these lines are nothing but the representation of the magnetic field. And you can see that the magnetic field evolves in the whole system. This we developed because we saw some interesting observations from our own payload on Chandrayaan-2. And to interpret those results, we have to do this modeling to take it to a good understanding of what is the physics behind these observations. So this is where the academic institutes and academic universities can help us in advancing the knowledge of the science in the Sun-Earth system. So finally, I'll conclude with my summary. sun is an essential source for life on Earth. I'm sure everybody would agree for it. And probably this is for all planets. Tomorrow, if you want to go and live on Moon or live on Mars, sun needs to be there. Without sun, you can't do that. And it also provides us to understand some of the physics which we cannot do it on ground, with normal conditions. Aditya L1 carries 7 payloads, 4 of them are remote sensing and 3 of them are in situ. Instruments are configured to take advantage of the missing elements, missing observations from other missions, and that is not available in near future. So Aditya will fill the gap between what is missing data available. Modeling is an integral part of the analysis of the data from Aditya. Of course, you can, many of you guys can help in that. And there's a plenty of opportunities for young minds like you to come in and help us to build the knowledge of the sun in better way. And all said and done, we always have interaction with the mission director here. We always have this constraint of per day, this much of data volume on B can be downloaded. Typically, we are going to get a huge amount of data every day, correct? So many of you who are interested in doing data analysis, automatic data analysis, AI ML based data analysis, you have a huge set of data which is waiting for you to look at it and analyze it. With that, let me thank the organizers for giving me an opportunity. Thanks a lot.
Thank you, sir. Thank you very much for the wonderful talk. And now I request Dr. Sean Saho to give the memento.
Take one at a time. Yeah. Thank you.
Thank you, sir. So from the morning, we have been having the wonderful sessions. Started from details about the Chandrayaan mission and Aditya mission and all the technical details and the science. So we are at the stage of concluding all these sessions, and then we have the interaction. There is small change in the program because of the few things. Now we will have a small concluding session, and after that there is a tea break, and after the tea break we have a dedicated interaction session which you can all of you can discuss with the scientists from ISRO, and you can ask all the questions whatever you wanted to ask. Sorry, we could not accommodate all your questions during the talks. And just one request, before going to the tea and just after the conclusion, we will have one group photo. Okay, so be stay here, and then after that, okay, thank you. So now I request Dr. Ritesh to conclude the sessions.
So I think let's first give a big round of applause to our guest speakers from ISRO. I think we all remember the historic day when we were seeing on TV screen this soft landing of Chandrayaan 3, and we enjoyed a lot and we felt a lot of proud. In fact, in IIT also we were projecting it on some screens and the whole room was crowded. So it was a wonderful, historic and proud moment for all of us. And listening from experts about these missions is a different experience. So first of all, I would like to thank all the people, Shrikant sir, Srinath sir, Bharat sir, and Shankar sir, to come here to accept our invitation and give us the time. We were actually trying to approach them since just after the soft landing, but of course, they are very busy in doing all data analysis, monitoring, and other tasks. But we are very happy that we could manage, and we would like to have more such events in future. So we request your support also, sir, in this regard. Also, I would like actually when we were, because in order to approach to people, we need someone to start the. So I'm thankful to my colleague, Dr. Arvinda, and he has a very good contact with one of his role model. Let me say, I came to know about this today, Srinath sir. So he knows him from his maybe before PhD days, and he's been inspired by him for research and other things. And thank you, Srinath sir, for helping us and bringing all these speakers and make it possible. It is really a great experience for us. In the same light, I would also thank students, faculty members, staff, particularly students from physics department and other departments of IIT. I know that students from ISRO and other universities also come here, and I can see a lot of students from various schools like KV Venkatagiri, Bharatiya Vidya Bhavan, Sainik School, Edify. They also come here, and I hope they have enjoyed the session. And I know they all wants to interact personally with the experts. That's why we will have a good time, and we will give you all the opportunities so that you can fulfill some of your curiosity. We'll do that. So thank you very much for coming and being such a good audience today. And this event would have not been possible without the support from students. So I would like to at least mention some of them who were working since last few days in making various things. I know many of the things I just post in WhatsApp, but these are the people who are behind and making them happen. So let me take the names. Satish, Mallikarjun, Rahul, Nirpend, Indu. They all worked very hard and help us in making this program in a very organized way. I would also like to, I think one of our speaker mentioned, and we felt very happy when he said internet is working very fine today. So I especially thank our computer center team to allow us to this uninterrupted internet so that the people who are watching remotely, they can also enjoy the event equally. So all the help from audiovisual team and computer center team for their support. I would also like thanks to our general administration for various arrangements. And at the last, I would like to thank the media, print media, electronic media for their support and coverage of this event. Thank you all. And what I'll request now, so I know that all of you want to have photo with experts. So rather than doing it in a scattered way, maybe what we can do, I request all who are sitting behind, they can come. There are a lot of empty seat here. We can squeeze in one frame and let's have a group photo. And after that, I invite all of you for a tea.